hope you'll have a very comfortable stay and enjoy not only the technical proceedings, but the rest of the activities on the campus. For this conference, 39 papers have been carefully selected with the help of the Technical Program Committee by the 3 co-chairs. I would like to now invite them to the stage. Professor R.K. Shamsundar, who is a distinguished professor in our department and head of the Center of Excellence, is indisposed. He's joining us online. Can we get that back? Can you hear us, Professor Shamsundar?
Yeah, I can hear you. Thank you, Shivakumar.
Yeah, so we will get you back online. And then I request Professor Yuichi Ikeda, Professor of Physics in the Graduate School of Advanced and Integrated Studies in Human Survivability from Kyoto University, to please come up on stage. I also request Professor Claudio Tessoni, who heads the Blockchain and Distributed Ledger Group at University of Zurich, Switzerland, to come up on stage. So I will now request each of them, starting with Professor Shamsundar, to say a few words. Professor Shamsundar, can you please give your...
Yeah, you can hear me, right?
Yes, we can hear well.
Yeah, thank you. Good morning. As already Professor Shivakumar, he is also a faculty on the Center for Blockchain Research and also one of the prime persons on cybersecurity from a long time, who initiated many cybersecurity initiatives. With a short notice, I was able to get him on stage. He's quite busy, and also the semester is ending, kind of a thing. Again, to repeat, on behalf of IIT Bombay and the Center for Blockchain Research and the BCK 2025 organization, I have the pleasure to inviting you, all of you, to the BCK 2025. I am sure the BCK, whatever the goals are, something like theory and applications are all moving in the right direction, and it will give a view how to go about a kind of a thing or the other. My apologies, due to some medical intervention, I could not meet you all in person, but I'm happy I'm seeing both Claudio, who is always in a very dynamic schedule of trips, and also Professor Ikeda, where is very scheduled kind of a thing, on stage kind of a thing. Hopefully, they have this summer, a nice summer weather in IIT Bombay, and also the vitality of the young people can be seen. And of course, Claudio can see the lake from his room, I would imagine, a kind of a thing. But particularly, I'm very enthused to see several Japanese persons participating. Welcome to them. They have come a long way to present their views and they interact, kind of a thing. Similarly, lots of people, including the Claudio group from Switzerland, that is Zurich, have done a wonderful job of participating, and they have been supporting the BCK for quite some time. Of course, the Ripple has always been a supporter for the Center for Blockchain Research, and we have also run a marathon, a hackathon here, and then on which the final presentations, the summary will be presented on the last day or the other. Also, there are many participants, including from our neighboring country, Sri Lanka, who are participating both at a student level and a faculty level. I'm very happy to see, and Dr. Vishwas Patil, who is a senior research scientist and also Bobita secretary to the center, who have been the backbone of making all the organization. And I hope you will have a nice technical view and also nice campus. You can interact with many people. Of course, lots of students maybe are off the campus kind of a thing. Thank you again. Wishing BCK all the success. Thank you. Thank you, Shiva.
Thank you, Professor Shamsundar. I invite Professor Ikeda to please say a few words.
Good morning, everyone. My name is Yuichi Ikeda. I'm from Japan. Actually, first of all, I have to thank Professor Shamasunda and Dr. Vishwas Patil and of course Claudio and for entire arrangement of the workshop. And also I have to say that all the participants to BCK25. Actually, 4 years ago, when we started the BCK21, it was a purely online academic workshop. But this year, many Indian researchers joined to this conference, and so I believe that they bring a new element from computer science and also many related areas. So we are growing technologically and internationally. So thank you very much for joining the conference. Thank you.
May I invite Claudio to please say a few words? Yes, we'd like to present a small token to request Claudio to first say a few words, then we'll give you the gift.
Thank you very much. It is for me a pleasure to be here. Thank you, Professor Shamasundar, for accepting to host this 5th edition of the BCK 2025 here in IIT Bombay. It is for us a pleasure. It is a collaboration that we started several years ago, also in the times of pandemic. I think that BCK started in Kyoto in 2021 as well in this strange online environment, and actually this is where we at the University of Zurich had our first contacts with IIT Bombay. And for me it was a pleasure to welcome Professor Shamasundar for a couple of years in our university, a couple of times, but then last year also participate in BCK and see the potential and the interest that this conference has, and they agreeing to bring it into this new edition into India. I also want to thank Professor Ikeda for, first of all, trusting us at the University of Zurich to organize the first edition that was outside of Japan last year. It is a very interesting conference. It's a very interesting conference that always brings together academics and practitioners from a completely different perspectives that makes the program very rich, and I am really happy about this. I really look forward, and I also thank the team, all Vishwas as well, Parminder, all the Akihiro, Om, Pierluigi, etc., all the people that was helping a lot in the organization during all these months that led to a program that I am really happy with, and I hope that you all, the attendees, can enjoy very much. And I also appreciate your commitment to submit your own contributions to this conference, because we know that it is very resource intensive to do that, and also taking the time and taking the opportunity to participate of the conference, something that enriches it. So thank you very much for being with us for this time, and I hope that we will keep seeing you in the next editions of BCK. Thank you very much.
Thank you, Claudio. I request Vishwas to please felicitate Professor Claudio. Thank you. So now we will start the first technical session. We will start with a keynote address by Titu Verghese. Can you please come to the stage? I'll introduce him, and then we can go step down and yes, feel more comfortable. Yeah. So it's my pleasure to introduce Titu Verghese. You can please have a seat. Who is a senior specialist in blockchain at NPCI, the National Payment Corporation of India, which I'm sure all of you have heard about. And many of you visitors to India may have started using UPI. So Titu is an employee of NPCI since 2019. He's a senior specialist in blockchain and builds scalable, resilient, distributed systems and blockchain applications for NPCI. He'll tell us about that. He's also the main architect for all blockchain-related initiatives at NPCI, at our payment corporation. Titu is a very active contributor to the open source ecosystem. He is the creator of Falcon, the Hyperledger Fabric Orchestrator. He is also the co-founder of a company called Servantire Global, which is a technology company focused on all future technologies. So I have great pleasure in inviting Titu Varghese to talk to us about, the title is The Journey of the Digital Rupee. Thank you. Our journey of NPCI.
Hey, thank you all. I think I am audible, right, for everyone? Yeah, perfect. So, I mean, most of you are familiar with NPCI. So, I was the one
I also wanted to thank Professor Shiwa for showing this conference. Thank you very much and hosting this opening session. Thank you so much. Thank you. Please. Thank you.
So thank you, Professor Shiva Kumar. So we had a good keynote speak from T2. I hope you all enjoyed. So now it's a time for start our first technical session. So I'm inviting the presenter. The title is Agent-Based Modeling of the Stellar Consensus Protocol. The presenter is Machita Picosi, University of Zero. Rude, maybe I'm pronouncing in a different way, Rude Biscoe Institute. So the stage is yours.
Great. Hi, everyone. I hope you can hear me. I'm Matija Piškorec from Ruđer Bošković Institute in Croatia. And I'm also a part-time postdoc in Blockchain and Distributed Ledger Technologies group at the University of Zurich with Professor Tessone. This is my first time in India. I'm really glad to be here. If any of you ever traveled to Europe and you're amazed by everything you see, even the most ordinary things, I have the same feeling when I come here. So this is the work done in collaboration with Jaime de Vivero Woods. He's a master's student at the University of Zurich, and Professor Claudio Tessone on the agent-based modeling of the Stellar Consensus Protocol. So just a short introduction. I'm actually glad that I'm the first one. First one in the technical session, so maybe I can just give a very, very short introduction of what actually consensus is in distributed ledger technologies. So if you think about distributed ledger, this is just a digital record of transactions, and I think that the previous speaker gave a really good presentation of the system which is actually working and it's actually implemented all of this. Consensus mechanism just ensures that all nodes have identical copies of the ledger. So consensus is basically ordering of transactions. So you have transactions which come from users, and then the way you order these transactions, some of them you can include, some of them you don't have to include, and in the ordering can be different. And the question is, if you have a ledger, which typically is structured as a blockchain, but there are other structures as well. You can have directed acyclic graphs as well. The question is, how do we update the tip of the blockchain? So this is the main question of what consensus is all about. And in order to implement it, you need two components. One of them are the voting rules, so how validators decides which updates to accept. And the other one is the Sybil protection, which ensures that the validators cannot easily create spurious identities. In permissioned or semi-permissioned systems, such as, for example, Hyperledger Fabric, you can have some form of a KYC. So in order to use digital rupee, you need to have this unique identity number which you get as an Indian citizen. In permissionless system, you have to figure out some other ways how to prevent people from creating spurious identities. And all of the known blockchain protocols, they implement consensus in some way based on these two properties. So for the voting rules, usually what's being used is either a longest chain rule, also called an Nakamoto rule, or some kind of a Byzantine fault-tolerant voting-based consensus with quorums. And in terms of Sybil protection, you can do proof of work. This is the most prominent example is Bitcoin. You can do proof of stake, which is Ethereum after 2022, and also many of these other algorithms as well, such as Solana, Polkadot, Tendermint. And you can try, so these are what are called the resource-based Sybil protection, where you actually have something to prove that you are, that you have a unique identity in the network. So in proof of work, this is basically energy. In proof of stake, this is the currency that is used as a native currency of the blockchain. But you can also try to use some kind of a trust relationship, and then this is called Federated Byzantine Agreement. And the Stellar Consensus Protocol and also the Ripple XRP ledger have this form of Sybil protection. And I will show you how we implemented the agent-based model for Stellar here. So Bitcoin is the first basically successful implementation of a distributed ledger. And it was underlying technologies were known for some time before, but Bitcoin was really the first one who put everything together. And now, of course, we have different architectures. So typically, DLT protocol have these different layers. So on the top, you have the application layer, where you have usually a language where you implement the logic. You have the Sybil protection, you have the consensus layer, and in the end you have the networking layer, which are more or less all of them similar. And Stellar recently has a particular smart contract language as an application layer. It uses the Byzantine fault-tolerant voting, and it uses federated agreement as Sybil protection. So just a short introduction, what is the Federated Byzantine Agreement? So it stems from this somehow old concept of Byzantine generals problem, is where you have the group of actors and they have to agree on whether to attack the fort or not. And they communicate between each other, but the communication can be lacking. Or some of the actors can be malicious, so they may not be up to attacking the fort together with you. So the question is how to reach a consensus of when to attack the fort. And this problem is actually easily solvable by a form of a majority rule called quorum. So basically you will commit to attacking the fort only if you see the majority of the participants committing as well. The underlying assumption is closed membership, so that you have the existence, first of all, you know how many nodes there are in the system, how many participants there are to be agreed upon. But the problem is, what if you don't know the number of participants? So this is a problem of open membership. And basically Stellar tries to solve this problem. So it's a federated Byzantine agreement system. Federated means that the voting is performed in rounds. In order to reach the agreement, there is no majority vote or quorum. Byzantine means that there is a presence of actors either giving a false information due to error or deliberate subversion, and agreement is just a word for consensus. So in Stellar, there are these explicit trust relationships, which, for example, you don't have in Bitcoin and Ethereum. Bitcoin and Ethereum used proof of work and proof of stake as a form of resource-based Sybil protection. But in Stellar, the trust is explicit, and it's defined in the form of what is called a quorum slice. Quorum slice is just a small collection of peers that you trust to convey the information about the state of the voting in the rest of the network. And the quorum is now constructed by iteratively adding these quorum slices between the nodes, which is called the quorum intersection. And there is very weak assumption on when is consensus possible, and that assumption is what is called internet hypothesis. So the only requirement is that these quorum slices are connected. So there is what is called a transitive reachability in terms of quorum from any of the node in the network to any of the other node in the network. This is something that's not enforced in Stellar protocol in the same way that is not enforced, for example, in the internet. In the internet, there is an implicit assumption that you can always reach any of the nodes of the network. And this is a self-emerging property, something that you don't enforce, but something that is satisfied in the system. I will not explain the Stellar consensus protocol in detail due to the time, but just a very short introduction is the basic building block is this federated voting, which involves multiple rounds. So basically, the Stellar consensus protocol involves multiple rounds of this federated voting, and some of these phases are called nomination and balloting. But basically, underneath is as a node, you start in the uncommitted, then you vote for a value, and then you observe what is happening in your neighborhood, and depending on this local quorum, you subsequently go through these stages where you accept and then confirm the value. And this happens many times in the Stellar consensus protocol, and this is just a short representation how this simple federated voting cascade works in the network of 7 validators, where eventually all of them will accept the same value. So for the agent-based modeling, we use the Gillespie algorithm, which simulates events. So the events have exponential distribution. This is just a diagram from a paper from our group, just to show that how to accommodate deterministic and undeterministic events. Deterministic events are the ones which happen at pre-specified time intervals, and the other ones is you just assume asynchronicity, that all events are asynchronous. In Stellar protocol, we kind of assume that all of the events are asynchronous. This is just the diagram of the simulator. Not to go into too much detail, the simulator is implemented in pure Python. It's available on GitHub. It allows us to initialize the simulation. There is a part where we go through the Stellar consensus protocols through all of these various phases. And because we are creating these artificial transactions in the system, there is also part which tracks the life cycle of the transactions as well. It's a command line simulator, so the output is just text. So this is an example of how the output looks like. Basically, every line that you see here is an event in the simulator with a specified timestamp, and it basically outputs everything that is happening there. So for example, this is an example of creating and retrieving transactions by the nodes, because the nodes are the ones who are retrieving the transactions from the mempool, and then they are combining them in order to commit them to the ledger. And then the nodes themselves are also exchanging messages, and these messages are events as well. And the messages are typical for the Stellar consensus. This is just some preliminary set of experiments that we did. This is actually not published yet. So we do have a couple of other simulators already in our group. So from some of the previous papers, we have a simulator for Ethereum proof of stake consensus, and we also have a simulator for proof of work. And the idea is of this project is eventually to do a comparative analysis of the consensus protocols. So these kinds of simulators, they allow us to do this comparative analysis in terms of scalability, in terms of memory bandwidth, resilience to failure, robustness, and so on. So this is some preliminary experiments that we did comparing the Stellar consensus protocol to proof of work, where we immediately see that proof of work has much higher transaction throughput compared to Stellar. Stellar achieves finality faster compared to the proof of work. So interblock time is mostly constant. This is due to the fact that Stellar has this fast finality, while proof of work is a probabilistic finality consensus. And proof of work exchanges far less messages compared to Stellar, and this is directly tied to the scalability as well. So these kinds of simulations we can do with the simulator. Long term, we want to answer the questions: how do different consensus mechanisms perform in terms of security, so robustness to various forms of attack, scalability, transaction throughput, decentralization, so what is the maximum number of validators. So, for example, proof of work accommodates much larger number of validators than there are in Stellar. So Stellar has around less than 100 validators, while in proof of work we have tens of thousands of validators. And then we can ask some other questions. For example, we can play with the peer-to-peer network between the nodes and so on. This is it. At the end, I just want to advertise two of the projects. So one of them is the project that I will be starting in 2026. It's a 5-year project in Croatia where we do investigation on autonomous agents in DLT ecosystem. So this is the first one. Currently, we are searching for a postdoc, and very soon we'll probably be searching for a PhD student as well. So if you want to work with me in Croatia, and also we collaborate quite closely with Claudia Tassone at the University of Zurich, you can reach out to me, and then I can share information about this. And also there is another project which is in a pipeline, which is not yet granted, but if it will be granted, we will know the decision in April 2026. We will be actually searching for 2 postdocs and 2 PhD students starting in 2026 or in 27. But for that one, we will notify you. So if you're interested in any of these positions, the first project is exclusively on the Ruđer Bošković Institute in Zagreb, with collaboration with the University of Zurich, and the second one is actually collaboration between Ruđer Bošković Institute in Zagreb and the University of Zurich. So if you're interested in any of this, I will be here for the rest of the conference, so you can reach out. That's it.
Yeah, if there are any questions. So if there are none, then we'd like to thank the speaker once more.
Thank you.
Thank you for the first technical presentation. The second one, the speaker is Vishwas Patel from IIT Bombay. The paper title is Programmable Money, Automating Social Benefit Schemes. So Vishwas is, yes.
Thank you. So first, one quick announcement. The Wi-Fi is working now, so you can
have this login and password. Please take a photo if you need to, or join in quickly. And then, as you know, we are running a little late, so all the scheduled programs are slightly slided. So we are going to continue in the same sequence as we have published online. Good, so done, right? So this is a work that we are doing at our Center of Excellence, and the idea is, as we have heard the first speaker today about the initiatives that the government is taking to explore the possibilities of programming the money, so that there is certain set of conditions that could be attached when the money needs to be spent. And government is a big spender in any country, and there are several use cases. So one of such use case I'm going to motivate and show you what we are doing in this space. So for the young students who are in this field, let me have the liberty to tell you what is this work about. So what is a programmable money? So it's a class of mechanisms that convert the general purpose money into a payment instrument that is acceptable only at designated places. So this is a condition, and it's talking about just a geographical location. It could be a specific set of merchant, it could be a class of merchants, and so those kind of things we usually invent, and you all might be aware that in our current banking or financial transactions, we know this instrument, instead of the general purpose cash, we use the check, on which we are optionally allowed to write certain conditions, for example, date on which it becomes effective. We put, if you remember, account payee only, that means it must go to the account first. It cannot be cashed directly. So these are the conditions we know how to enforce on a payment instrument. So this is in physical world. So we are exploring what are the alternatives or what are the current state of affairs in the digital world. So that is something we explored, and we are telling you the approach that we have taken. So usually what happens, so such instruments go to the bank, they get settled over there, and they have a set of protocols that they follow. So usually all these are well documented, well followed set of instructions that we do, and the money reaches its destination. So that is in physical world. If you are aware of GIRO, which is General Interbank Recurring Order, which allows you to do something similar. For example, your electricity bill, mobile bill, house rent, etc. kind of instructions you can give to the bank, and those will be periodically settled. So there is a condition of time, there is a condition of a destination, there is a condition of for what purpose it should go. So such things are allowed in your net banking interface. So similarly, Government of India has NACH, which is Aadhaar-based conditional clearing house for payments like Manrega, etc., and a lot of other things. Then in private space, you might be aware of instruments like Sodexo and private coupons like or the FASTag, which is specifically for transport purpose in India. So these are the examples of how we put conditions on how money should be used for certain purposes. So you are free to imagine, given such conditional expressibility, what you can do with money. And if we extend this logic, and if we boil down the question to what are the options to program the money as of today, and what can we do with this? So that's what our presentation is about. So in the check example, we have seen the conditions like time and the destination account number. can we put additional causal conditions? Let's say, what if it is a particular condition, let's say in terms of insurance. We don't know when an event occurs, when the accident happens or when the unfavorable condition occurs. But when that event occurs, this money has to be dispersed. So this is the condition. So does our current instruments allow us to express such thing? No. But does blockchain allows? Yes. So we are exploring that all the instruments that are invented so far, including blockchain, what can we do in terms of programming the money? So using smart contracts, we can do many things. We can do a lot of complex logic, but as we know, these things also come with certain risks. So we have done some work in the past, which is called land management system, in which we explored how we transfer land ownership from user A to user B using blockchain. So we are extending that work to further make it a general purpose protocol beyond land asset. So can we express conditions like insurance settlement, auto disbursal of government schemes to the beneficiaries? So as we know, there are a series of inventions of cryptocurrencies, and all of them came with very unique proposition that they solve. So Bitcoin is a token-based point-to-point UTXO kind of protocol, very simple, no complications, no accidents so far. Then came the Ethereum group, which motivated the space that can we put conditions, can we have contracts, can we have general purpose asset allocation? And yes, it is quite matured, we can do so, but it comes with several serious vulnerabilities if we are not careful with the contracts. So in our work, whenever we want to propose a protocol to government schemes, the first question that comes to us is, can we give the guarantee that it will always work, and who takes the ownership? So as we know, it is difficult to give the guarantee on general purpose programs about their correctness, which is also true to some extent on smart contracts. We were inclined to stay as close as possible to script-based programming, like the UTXO of Bitcoin. So we took Litecoin protocol and we modified the Litecoin protocol and added some more scripts into the protocol for the specific purpose that allows us to express our conditions to program money. So earlier we had extended this Litecoin protocol for land transfer. Here what we are doing is we are doing it for direct benefit transfer schemes of the government. So typically a DBT scheme that are India is a huge DBT transaction-wise. If we see, we have around 365 crore transactions per month in DBT in India, and around 30 to 40 US billion get credited to eligible users' accounts every year. So that's a huge amount. And in the past decade, the government, just by introducing stricter identity mechanisms, could plug the leakages in the system. But what we are motivating over here, that given a programmable money feature into this scheme, we can do further improve efficiencies, and we can figure out cross-department leakages. Means there could be a beneficiary who is taking benefits from multiple departments, and since two departments do not reconcile their transactions at a single place, such leakages do occur. So the intention of this work is to give these three functionalities. can we allow the departments to issue tokens, how they should be used, and what should be the reconciliation mechanism. So since there are several instruments like color coin, etc., which as in the first speaker was mentioning cursorily about government has intention to give subsidies like fertilizer subsidy, etc., which should be, or scholarships, which should be used only specific for those purposes. So whoever is giving those services and collecting those tokens, they should be allowed to unlock those tokens and go convert those tokens into general purpose money again. So these kind of programmable lock unlock features are expected in these instruments, and that is what we are experimenting with. So as I mentioned, these are general expectations from any scheme, but let me be brief over here. The overall architecture is like this. So we have a main chain, which is on the right hand side, which keeps only the metadata about different departments and their transactions. So if you want to say whether person A has a particular benefit received or not, it could be binarily checked on the main chain, but about the intricacies of what all conditions have been achieved or who has signed on that particular dispersal, etc., is kept on the side chain. So since India is a federal structure, different states have different eligibility criteria, different set of protocols to execute those dispersals. So we need to give that kind of operational flexibility to the states. So side chains are represented by states. So this is how technically the architecture looks like. So we have modified the Litecoin protocol. We have a set of whitelisted miners. Since Litecoin works on proof of work, we modified the proof of work, reduced its difficulty level, and we allowed only the whitelisted public keys to do the mining. And once that is done, we allow the side chains to invoke the represent the states, and then we anchor those side chains on the main chain. So, and at the identity level, we have the Aadhaar interface. So this is a broad architecture of our DBT implementation, and these are the different transaction types that we have designed inside Litecoin. And we don't give a general purpose interface, smart contract interface in our implementation in the main chain, which remains a script-oriented chain, but the states are allowed to implement their own side chains, and they can take the ownership of their respective business processes. So that's what we do in our DBT protocol using programmable money. So when the government allocates a particular budget for a particular scheme, the whole amount is programmed. It is defined where it should go, and the conditions are provided, who are eligible people, what should be they need to be done, and that is the issuance part. In the usage part, the conditions will be checked, and in the reconciliation part, the money comes back as a general purpose money. So it starts as a programmed money or programmed token, and when it reaches its destination, it gets reconciled as a general purpose money. So the loop completes. So that's what we do in this protocol. So for more details, we can discuss it later offline. So any questions? Good. So we'll start with the next. You have a question, Claudia? It's a script-based protocol, and
What it has different from Bitcoin, for example, because from my company perspective, it's more or less the same.
yeah, we could use that either.
Okay.
Yeah.
Thank you.
Yeah.
Thank you for the presentation from Vishwas. The final presentation of the technical session 1 is distribution and analysis of cross-chain, token transfer latency, and estimation of validation count dynamics in Ethereum Polygon bridges. The presenter is Akira Fujihara from Shiba Institute of Technology. So is Akira's stage is yours.
Yeah, counts. Yeah, it's okay. Hello, thank you for the introduction. I'm Akihiro Fujihara from Chiba Institute of Technology, Japan. Today, I will present with this title. And this work, this is collaborated with Tao and Claudio from University of Zurich, Switzerland. As you know, in recent years, the number of Ethereum layer 2 networks has rapidly increased. So cross-chain token transfer interoperability has become an essential research topic. As you may know, offshore bridges typically allows tokens to be freely moved between Ethereum and its layer 2 networks. So user can deposit token from Ethereum to layer 2 network and then withdraw them back after they use decentralized application, and if the token on the layer 2 network is left, they withdraw them back to the Ethereum. So there are many layer 2 network, for example, arbitral optimism and Polygon and so on. In this presentation, we focus on Polygon network. Among these layer 2 network, Polygon is one of long-standing and widely used. Polygon provides an official proof-of-stake bridge which implements a lock and mint, burn and release mechanism, which I explain later. And Matic or POL tokens are issued on Ethereum. This can be transferred to POL on Polygon network. In this slide, I briefly explain about the lock and mint and burn and release mechanism. About lock and mint, this is related to deposit transaction. On deposit, tokens are locked on the source chain. In this case, source chain is Ethereum, and the equivalent amount is minted on the target chain. In this case, in Polygon network. About burn and mint, it is related to withdrawal transactions. The tokens are burned on the target chain, in this case Polygon, and the equivalent amount is released on the source chain, in this case Ethereum. As you may know, Ethereum's block generation time, or block time, is approximately 12 seconds, while Polygon's one is about 2 to 3 seconds. Nevertheless, the deposit token transfer time takes more than 20 minutes, which is too slow compared to block time in Ethereum and Polygon. What is the dominant factor that determines this token transfer, deposit token transfer time? Of course, this time changes based on the congestion on the source and target blockchains. But on average, yeah, I also checked this time. Actually, I transfer my Ethereum to the Polygon network and withdraw token to the Ethereum. And so I also checked this long transfer time. A previous study done by Yang et al. Analyzed historical transfer time on Polygon proof-of-stake bridges. Yeah, this is the paper. And they pointed out that the main bottleneck is Ethereum network finality. Those who are not familiar with this term, I briefly explain about them. Network finality is the assurance that the block, once confirmed, cannot be reverted. And also finality time is the time required for a newly generated block to reach network finality. So several important questions remains open now. In this work, we would like to address these three questions. First one is, why is network finality critical in bridge network? And the second one is, what is the precise breakdown of token transfer time? Or how do Ethereum, Polygon block times, and network finality contribute to token transfer time? Third one is, can we empirically verify the real data that network finality is really the main factor that determines the token transfer time, on average 20 minutes. So in this talk, our contributions are threefold. Just I read this sentence, but we clarify the security rationale on Polygon proof-of-stake bridge. Actually, to prevent cross-chain double spending attack. So the bridge system bridge system required that source chain must finalize the transfer-related transaction. By reviewing the behavior of proof-of-stake, Polygon proof-of-stake bridge, we show that bridge intentionally waits for Ethereum finality before minting asset on Polygon. And by analyzing existing measurement data of deposit transfer times, we demonstrate that mean and standard deviation of token transfer latency can be used to estimate increasing trend of Ethereum validator counts, which we mainly analyze in this presentation. Next, I would like to talk about the security to avoid cross-chain double spending. Cross-chain double spending is an attack that an attacker uses tokens on the target chain, then forks the source chain to erase the original locked transaction. If this attack succeeds, the locked token on Ethereum reappear, reading duplicate values, degraded token values. To prevent this scenario, as I mentioned earlier, the source chain must reach finality first. Only then the target chain can safely mint the token. Guaranteeing finality, network finality is essential. Next, I would like to briefly explain about the Polygon proof-of-stake bridge architecture. In this talk, we focus only on deposit process. We haven't done consideration on withdrawal process. So we focus on deposit only. In deposit process, deposit transaction is incorporated in Ethereum blockchain, which approximately takes 12 seconds. The system waits until Ethereum network finality, which is about, on average, 20 minutes. A Polygon relay network called Heimdall layer. In this layer, manages blockchain, so they can make consensus using Tendermint, or the actual implementation is Comet BFT. Comet BFT is used in this Heimdall layer. So this layer processes the state sync and mint the tokens. This is on average 2 or 3 seconds. So deposit token transfer time on Polygon proof of stake bridge is the finality time on Ethereum plus block time on Polygon. Since block time on Polygon is very small compared to the network finality in Ethereum, so finality time on Ethereum dominates this token transfer time in Polygon proof of stake network. Then to demonstrate this consideration, so finality time on Ethereum is dominant for the token transfer time, we use the data set collected by Yang et al. They achieve about 95% matching accuracy for deposit from Ethereum to Polygon, which is great. And the period I used in this analysis is September 2022, which is the start of the Ethereum March. After until the August 2023, we compute the histogram of token transfer time in 4-month slicing window. Why I select 4-month slicing window is to aggregate sufficient samples to compute natural histogram to analyze the statistically. We have evaluate both. I'm sorry. Yeah, we evaluate both mean and standard deviation of token transfer, the deposit token transfer time window, and to see the time evolution of this T. And we hypothesize that the bottleneck of finality time is the broadcasting of block information and its voting results among validators. So during the finality time, there are multiple broadcasting process between validator nodes. So this, we think this is the bottleneck time to analyze a network finality. And our previous work, we developed a continuous time Markov chain-based mathematical model of the broadcast time and the finality time, which is explained in details in this paper recently published in Distributed Ledger Technology Journal. And by using this result, we obtain the mean of finality time is proportional to n log n over lambda, where n is the number of validator nodes, and lambda is the average communication speed between validators. And also, the standard deviation is approximately n over lambda. So when the number of validator nodes increase, both mean and standard deviation increases. And by using these results, we try to estimate the number of validator nodes on Ethereum. Interestingly, we can perform using the token transfer time on the Polygon POS bridge. So, as I explained, mean and standard deviation is like this. So, just so calculating the mean divided by standard deviation is approximately log n. And by using this, n is proportional to exponential mean divided by standard deviation. So based on this simple calculation, we estimate validator count using the Polygon proof of stake deposit transfer time. And the result is like this. So this is the time evolution of estimated validator count. So after, in 2023, the estimated validator count increasing. And we also get the real validator count data from Beacon Chain Explorer. And we compare our estimated result with this real validator count. And result is this in the correlation plot. And we observe strong correlation with Pearson's correlation coefficient about 0.87, which is very strong correlation. And this value provides a fast empirical evidence that cross-chain bridge latency is shaped by validator count dynamics on the source chain. Then we briefly discuss a fundamental trade-off regarding bridge. There is a fundamental trade-off in Polygon proof of stake bridge, and maybe other layer 2 bridges are similar. Increasing validator count improves decentralization and security. Of course, the number of validator nodes is large. Then decentralization is realized. And because many validator nodes stake the token, the security is also increased. But at the same time, as I show the data analysis, a large and increase both the mean and standard deviation network latency. So the token transfer latency is also increased. By this observation, maybe this is too early to conclude, but in general, the bridge cannot be simultaneously very fast and highly secure. Let me conclude this talk. Polygon proof of stake bridges. Approximately 20 minutes delay due to Ethereum network finality. And this is not related to Polygon network. I haven't explained the number of validator nodes in Ethereum yet, but as you may know, the number of validator nodes in Ethereum is the biggest, largest among the blockchain project. So I forgot the exact number, but maybe 1 or 10 million validators are there in the network for each validator stakes Ethereum. So which is the source of security. But because of this security, the bridge transfer time becomes longer and the longest. And we also we explained that delay is a security feature to prevent cross-chain double spending. And using the token transfer data set, we can estimate Ethereum validator count dynamics, showing the bridge latency fundamentally reflects the source chain's property. There exists an avoidable trade-off. This is my hypothesis, maybe, but maybe there is a trade-off between security and performance in bridges of blockchain network. Yeah, there are many future work that we have to do, but yeah, I raised 3 here, but maybe I don't have much time. So I will conclude my talk. Thank you very much for your kind attention.
Yeah.
Thank you, it's nice talk. Maybe it's related to what you listed here. Because I'm just wondering, right now you have the data set from the 2022 September, right, and 2023 September, which I think that when you check the price, if I'm not wrong, the price is rather stable. But if you compare the price maybe like 5 months earlier and 5 months later than your data set you have, you see like the price, it's increasing. So basically you have more congestions and more traffic in the network. So my questions would be, this 20 minutes that you found, it's just the average on this particular range of time. But if you extended the data set and then you have maybe like some kind of like outlier transactions that, I mean like the numbers of transactions become larger and larger, this 20 minutes won't be the case anymore. So will the model you are fitting, it's, I mean, it's applicable or not? That is one. And the second one, yeah, I related to, you said like now you have this
actually,
one.
I want to answer one by one because
Sorry.
I tend to forget. Yeah, thank you very much for your question. So this theory is very general one, so we can apply almost every bridge protocol. And actually, this time we are interested in the number of validator nodes. But as you may know, that there is also another parameter, lambda. This is the average communication speed. We can estimate this lambda using this scheme because we estimate the number of nodes like this in the equation below. Then using this n estimated, and maybe you can use both so mean equation or standard deviation equation by maybe divided by, so maybe for example, this exponential mean divided by sigma divided by sigma. We can estimate the lambda so that we can estimate the average communication speed between validators. So I haven't
So my
analyzed
question,
yet,
because
but
now you have standard deviations
then-
in your expressions. That means like if your data set spread out very widely, these standard deviations play some roles.
So I haven't checked the price change, but if well, we can get the price change, and also we can compare the estimated average communication speed, time change of average communication speed. This is what I want to explain. And I forgot one thing I want to say, but does this answer your question, the first question?
Yes.
Okay.
Yeah.
Thank you. Maybe I after that I remember I'll talk about. So next second question is.
Actually, next question is what exactly what you listed. Because of now you have just one-way transaction from Ethereums to Polygons. How about like you having like a dual transactions? For example, you have one from Ethereums and the other one from Polygon backed. You already listed.
Okay.
Thank you so much.
Yeah, thank you very much for the question. So we haven't analyzed withdrawal transaction, token transfer time, but Tau, so the previous work analyzed the median cross-chain transfer time, and they show that the token transfer time tend to be larger compared to deposit transaction. But we don't know the reason. Maybe using this scheme, we can explain this. So this is one of my future work. Thank you very much for your question.
Maybe we can take it over the tea. So we are quite late. So let's thank Samantha, the session chair, and the author for concluding. We are running quite late, so quick announcements. Those who are not familiar with this place, there are restrooms just beside the auditorium, in the corridor, and in the adjacent building also. You ask outside somebody, you will get help. And then we are breaking for tea now for 20 minutes instead of 25 minutes. So we'll recover 5 minutes. And in the next session, we'll try to be quick, which is going to be chaired by Om. And then our lunch is around 1 to 1:15. And we'll again make an announcement when we will reconvene. So we are breaking now, and we'll try to reconvene in 20 minutes, which is exactly, it is 11:45, let's say, right? At 12 we are reconvening. So let's reconvene at 12 o'clock, next session, 12 o'clock. Okay, thank you. So the tea is behind. Okay, so we can use these two gates.
welcome back, everyone, after the tea break. Do we have everyone in the room now? Okay. It's fine. I can stand here. So welcome on the second sessions on technical sessions. The first speaker today will be the first speaker. It's Samantha Tarina Jayakumar from University of Jaffna. So please, the floor is yours.
Good afternoon, all. So hope you had a good tea. So myself, Samantha, from the Department of Computer Science, University of Jaffna, Sri Lanka. So thank you for the committee giving the opportunity to present my ongoing work. So this is an agentic AI framework for knowledge graph-based blockchain network analysis. So this work is actually the continuation of my PhD, I could say. So these are the overview of today's presentation. So before start my presentation, I wanted to set the motivation behind this research. So you may heard about the illegal activities happening throughout the blockchain. So blockchain, it has cute properties like it's decentralized, immutable, and it secure the privacy of the users. Even we heard from the keynote speaker as well. So somehow this is using by the illegal actors, like those who are intended to hide their illegal asset, like the black money or drugs, or they earn the money, but they try to hide throughout the public blockchains. So my work based on the Bitcoin and Ethereum. So the intention is how we can, which pattern they are doing. So then, because when they deal this kind of things, the problem faced by the financial regulators or the forensic analyzers. So if they wanted to make the people to trust and use the blockchain, they need to regulate somehow these things. So they want to learn like how this happening, like what pattern. But what's the barrier in the blockchain is, we all know like it's decentralized. So there is no mediator and he can't monitor like who is behind the scene. And also the data also, it's not the understandable one, like the users can't, by looking at the data, they can't say this is happening throughout the network because it's complex. And there's no user data, like we don't know like who is the user, only they have some hexadecimal addresses. So whether this is possible for them to analyze, so my intention, my end users are the forensic analyzers, regulators, those who are working in this kind of field. So that's how we, but the existing work, they are also, I'm not the first one doing these things. So there are existing work. So what they are doing is like they collect the transactions and applying machine learning. Then they try to understand like what's the relation between these labels and the features. Or they model them as a graph or based on the heuristic, like if it is money laundering, this is the pattern, it looks like this. But the actors is smarter than us, right? So if they know the pattern, this pattern they are monitoring, they can change that pattern as well. So in that case, the heuristics will be fair. So that's how the existing approaches, they are doing well, they are giving the predictions with 99, but what they make sense for the end users, those who are intended to understand what's happening throughout the network. So if we choose the blockchain, like it doesn't have any reasoning, but machine learning model, whether they are explainable, they are telling why they are predicting this wallet looks like suspicious. So that's the other question, but their intention is they wanted to know. That's the evidence to prove this account is malicious, this wallet is malicious, or this smart contract is malicious. So that's how we can do that. But they are having graph-based patterns, whether they are open for, like, whether they have the knowledge, which means our end user is not the blockchain expert or the computer scientist to understand, or the query from the graph, whether they know graph queries to do that. So that's the question with the existing system. So how we can overcome, so that's the proposed methodology. So if you are the investigator, you may be interested to analyze about the wallet. You may ask the question like, can you tell about this wallet, which wallet it's interacting with this wallet, or how many transactions happen during the month? That might be the general way of, native way of question. So that will transfer to the LLMs, the language model. Then they can convert that as the query. It's based on which knowledge we are using. So in my case, I use the graph database. So then they transfer that thing to the human native, like the query give the subgraphs. Then from the subgraphs, we can apply the machine learning model and give the score. So then we get back those things again through the LLM and generating as a report of evidences that will send to the end users. So that's the all purpose of this framework. So let's see one by one. So the data collection for my research is based on the public chains, so Bitcoin and Ethereum. So it's both we install the node as well as from the available label wallets. So there you can find from the Bitcoin info or Etherscan, there are some suspicious wallet they identified. Off-chain record, maybe if you are the forensic analyzer, you may have some label addresses or you are intended to know about the address. That's the off-chain things you may have. So then that can be modeled as a graph. So based, you can visit these couple of papers we have published. So how the blockchain data can be modeled as a graph. So we propose the approach for both UTXO as well as the account-based data. So I worked in both. So the nodes can be the wallet transactions, or it can be a smart contract. So it's basically it's a heterogeneous graph. So if you take a Bitcoin network, the wallet will be there. From that wallet, so this is a sample graph for related to the ransomware settlement. So in here, the orange circle, they are the wallet. So it's in your right-hand side. So they are the wallet, and the blue ones are the transactions. So I only have the label for the middle orange one, that is the ransomware attack-based illegal gains it's gathered. So the red arrows, it's actually pointing to gathering. Then the green ones are spending, actually. So they spend it to the wallet. You can see it's a gathering wallet, but it doesn't have any label. But that's the wallet holding this illegal asset. We only have a label for the middle one. So we don't know where it is going, but somehow this subgraph shows that pattern, like how this money flows and how it is accumulated in one point. The one is in your left-hand side is for the Ethereum network. So in this graph, you can see the middle one is the smart contract. You all may heard about the Fonzie attack. They announced, like, if you invest, we will give more money. Then they closed that smart contract. So at the end, there's nothing. So then people only lost the money. So this is related to that smart contract. The same way the smart contract is in yellow, and the transaction related to that smart contracts is in blue. So this is the subgraph. So from this point, what we can do, that's based on the graph knowledge. It's a graph database I was built. So then what we can do, like we can use the LLM. So in here, let's say your question is, can you show the wallet that received in last 30 days or 3 hops, in the sense the length of the chain is 3. So the model, the LLM can, the intent is we need to know the transaction flow. Then we have some slots. So one is the which address and how long you need, how many hops. So these can train through the language model. So then that will convert this natural query to the graph query as shown here. So then what's the point, like when we can use this query to query the knowledge of the graph. So then it will give you the subgraph. So the subgraphs, we can apply the temporal graph network. So why I choose these two is the address is changing, because blockchain network is the evolving network, is not just you can keep the static and you can say this is wrong. You need to evaluate them time to time. So that's the reason why we choose the temporal graph network. The first one, it will say based on the history whether this wallet, it will give the score for the node. So based on the history, which means like how many transaction is doing, how many wallet it's interacting, or how many smart contracts is calling, then we can have a score for that. So then the second one, it will do the time to time. It's a real-time analysis it will do, and it's going to give another score. So these are the evidence for the users we are going to give. Now we have these things. Though this will send back to the client as a report. That also will do with the help of LLM. It will be documented as in a proper way. So we can generate a report. So that report holds the subgraph patterns. Also, they're going to show the scores. Then the regulators have the evidence of why this address is the malicious. So they can prove that one, or they can regulate these transactions. If something happened like this, then we need to be careful. So the awareness will created for them. So that's the whole idea of this framework. So we are up to the graph things, and this is ongoing things. And in the conclusion, so you can see that maybe I try to convey this, what I try to propose. So open for, I'm happy to answer if you have any questions. Thank you.
Thank you so much for the nice talk. Any questions?
Okay, thank you very much for very interesting presentation. I have a quick question for you. If I understood correctly, you are analyzing the past data to extract malicious transaction. And that might be deeply related to price change, right? So, but my question is, by understanding the past history of the transaction, how can you detect the future ongoing price change? If the some serious situation might happen in the near future, can you detect the future change? This is my question.
So if I'm correct, like the price changing activity, so it's relate with the time, right? So let's say we are, that's what I have shown that graph neural network. So it will analyze the history, so which means when the graph is built, then when it is evolved, which means the wallet, the transaction is vary, then that will capture by the second one. So that will get the things based on the time. So then the score will be changed. So that will give that time-based changes for the wallet. Then that makes sense for whether it's suspicious or not based on the score.
Okay, but this is a traditional econometric approach. Same thing was happened in the econometric study. They are looking for, they want to forecast future by looking at the past. This approach always failed, unfortunately. So I think this approach is very interesting. So you might need some trick to change the situation.
Yeah, okay, thank you.
Very nice.
Thank you.
Oh, thank you. Unfortunately, we have no time for the next one. So thank you so much for the speaker. The second speaker will be Abhijit Pasi. She's in the room. Ah, okay. Lovely. So, please. So he will present in the topic of solving the blockchain trilemma with a dual layer proof of stake and proof of ET consensus framework. So please, the floor is yours.
No, that's fine. New promotion. It's a PPT. Yeah, I can. Should I mail it? Pen drive. तिथून लूज झालं का बघा. Cable. Use with cable. Same problem.
It's coming then going.
So we want to connect one sec. We want to
Remote?
yeah, appreciate it. I also did it twice. Yeah, just a sec.
Works actually, yeah.
Same thing happened with my laptop.
I-
It will disappear, sir.
Oh, it's coming. It's came. Which one? This one? Oh, you can.
Okay, sorry for the technical glitch. So myself, Abhijit Pasi, I'm a PhD student of KJ Somaiya School of Engineering, and this project is under the collaboration with Center of Sustainable and Secure Blockchain Development, which we call it as the Euclid. So this is the outline of the presentation, that we will see the introduction, problem definition, problem statement, a proposed solution, then the architecture. We'll see how that layers interact, security threat models, probably some results that we have been captured in Python basically, and then performance evaluation followed by future work, conclusion, and the references. So when it comes to blockchain, so as they say, like we are trying to improve the blockchain trilemma. So when it comes to blockchain trilemma, we talk about certain things like scalability, security, and decentralization. It is often said that no no algorithm, consensus algorithm can solve the blockchain trilemma. So we were pretty much hypothetical about the same, but as the reviews we received, we believe that we just scale down to a bit, and we'll try to improve the current blockchain trilemma. So The problem statement says that existing consensus mechanisms struggle to balance between the three triad, that is centralization, decentralization, security, and scalability to some extent. When you say that POW often gives the scalability, it is the most secure and centralized stuff, decentralized stuff basically, but then it often lack with the scalability. So you may have learned that we got 7 TPS per 7 transactions per second. Often we see that. When it comes to proof of stake is good. Where it gives a good number of transactions. It is scalable. It is secure to some extent, but then often we say that the person with the highest credibility or highest token will get an opportunity to mine it. So that triggered me out, like how I should proceed with my PhD, and I thought about going about merging both POS and POT, because then POS will give me the architecture of security, scalability. When it comes to POT, it's a random time evaluation, and based on that, we will be in a position to get the decentralized. We can achieve the decentralization better. So that is how we'll try to improve. Now the proposed solution, we say that there are dual layer where the response will have been separated. So the framework separates the functions of economic security that will be handled by purely POS layer, and followed by the fairness will be handled by the POET. This will definitely improve the scalability and decentralization, and that's how we can balance the trilemma, making sure that the security pattern will be inherited from POS. The basic POS limitations are POS basically works on the token age. Like the older the token that you have, you will get an opportunity to mine the existing block. So that's the basic problem with POS. Then we need to tackle, because that will actually come up with those old seldom item that says richer will get richer. So we are using POT just to have the fair leader selection. We are going to use the TEE, Trusted Execution Environment, followed by the SGX Software Guard execution, and which will give us a low latency, and the decentralized, which is equitable to the proposed work. Now this is how the architecture basically works. When I say architecture, the layer 1, which has the POS, which where we can the validator set and the stake management, followed by the economic security or scrutiny, followed by slashing and admission. So if I have the hundreds or thousands of miners available in the pool, we can actually segregate. Out of those 100 or 1,000, we can have n number of pools, which will be validated pools who are willing to keep X amount of stake for the particular block. And then POET will give the random numbers, that is random sleep time to all of the validator. The validator which has the opportunity, or whose time will elapse first, will get an opportunity to mine the block. The moment the POET block or the selected validator mines the block or completes the block will be broadcasted as we do in a normal blockchain. And then the others, remaining n-1 validators will actually validate the block. If they found that things have been good, we will do it. So that will actually leads up the instant finality, followed by no forking issues. So this is the response that we have already seen. Now how the layers interact. So POS to POET, the POS layer will actually have the validator sets, as we said, that number of validator that we'll be using, followed by the stake weight, that the weight that each validator are willing to stake, just to make sure that there aren't notorious validators, followed by the slashing information. See, if any validator provides any notorious activity, then the slashing amount, like what percent of amount stake will be slashed, so that will be provided by the POS to POET, wherein POET will see the leader selection. So amongst the n number of leaders that you are having, assigning the random numbers with the help of VRF or VDF that we are yet to finalize. And we are also going to incorporate BFT, just to make sure that 2 by 3 plus 1 validators we will be using, just to make sure that instant finality can be achieved. The security and threat models, like we say that risk in POET, obviously POET has the TE vulnerabilities, that is trusted environment execution. We don't want to have the single or centralized person like Intel or SGX. So will be going with the Intel, AMD, Ryzen, just to make sure that the TE vulnerability can be overcome. followed by the network issues. So whatever the delay or manipulation the network messages can affect the fairness, we will try to that may disrupt the POET timing. Stake attacks, so we can have the attackers with the last stake might try to manipulate the leader selection or exploit the POET. So basically it's a probability based activity, so POET randomness may get compromised, and that will have the unfair advantage, but the POS will have the protection over that. So POS layer will act as a safeguard that ensuring that attacker in the POET layer do not compromise the overall system security. So they can perform the validator's eligibility followed by the stake mechanism. How like in case of the faults in POET can be contained with the help of POS safeguard again, which will provide the protection against the economic security, and then the finality can be taken care from the POS. These are some simulation results that we have gone. It's a Python simulation just for my APS and IPS. So you can see like the dual core manages the pretty much even Steven throughputs, and then when it comes to the finality, we get the even Steven finality. When it comes to impact of TE compromise, you can say that the POET versus our approach, we get the better secured what you can say leader fairness, and followed by this, excuse me, yeah, the attack. So when it comes to attack, you can see that based on the attack or the type of attack, the slashing rates can be compromised, like 25%, 50% or 100% of the stake that the user actually staked upfront. So when it comes to performance evaluation, the impact of compromised POET, the leader selection, if the POET is manipulated, it may allow certain validators to gain the leadership opportunity, but this may not happen directly or directly threaten the integrity, because most of the time things have been taken care by the POS layer. So basically we are trying to work with this consortium blockchain. The throughput comparison that we have seen, that we try to get the trade-off between the other POS and POET, we try to get the trade-off between that. In case of leader selection or leader fairness, by the time when you start with the mining, nobody is knowing who is going to be the next miner, so they will be using ZKP, zero knowledge proof, just to attain the activity or the authenticity of the time elapsed. Security maintenances, even though the performance is gained, the dual layer system continues to maintain the POS level security, so which can eventually virtually accepted. So the risk that are handled by the dual layer proposal, that throughput comparison that we have seen, it tried to find out the trade-off between the POS and POET. The leader fairness has been accumulated or verified at our end with the various validators like 32, 64, 128. So we have tried up to 128 validators. When it comes to security maintenance, again we are going to attain the POS level security. TE compromise handling, so if the TE compromise is handled by the system, POET may have the biased leader selection, but the economy security maintained intact. And the system stability, POS continues to enforce the validators eligibility and fairness in selecting the leader. So how we can improve, like we are trying to improve the scalability. The dual layer design will increase the throughput as opposed to POW and POS to some extent. Again, when it comes to decentralization, POET randomness will give us the decentralization followed by the security and finality. The key parameters that we will be catering in terms of deployment, so slashing level, we may come across different slashing layers, and then balancing the security, performance and fairness to attain the optimal performance. The future work that we will be catering in next 6 months or 1 year probably. So dual layer framework, so we'll introduce the balance approach to address the trilemma, followed by the blockchain design that we can look after. We know that this is not a complete solution. We are not able to solve the blockchain trilemma, but we will definitely try to provide a better solution which balances best between the core aspects. integration with the modular architecture, so we will try to do that. We will work on the POD timers by integrating VDF and VRF, sharding and roll-ups that can be catered, and dynamic POD adjustment based on the network congestion or network traffic. So the conclusions are like this. These are my references, and I would like to thank my guide, Dr. Irfan Siddhavatam, who has played a pivotal role, followed by Dr. Ashwini Dalvi, who has been into it. She is a part of Euclid, Dr. Nilkamal More, and Professor Sagar Kode. So these are the things like.
Thank you, Abhijit. Is there any question?
Thank you for the presentation. I have a question that, because you used several times the term fairness and equitable in terms of the validation power that is. Can you please elaborate more on what you mean by that?
Okay, sir. So when it comes to proof of stake, in this entire auditorium, we believe that there are few numbers of validators are like you, sir, ma'am, the key chairpersons. Those are the highly staked people. So if we consider all of us are the validators, so you people are the most respectful and the staked people. So when it comes to a new job, I will try to give my job to you. So over the period of time, the students out there, they may not get an opportunity. So when I say the students out there, they are the lower miners or lower validator. They will not get an opportunity to mine the block, and as a result of that, they won't get the stake or the reward that has been catered for them. So that is the problem of proof of stake, which we call it as centralization. Okay. Now when I say fairness, the moment we say that I have these 50 people over there who are willing to mine or willing to participate, we can say like out of 50, out of those 50, 25 people are willing to stake $100 as a part of staking. So if any notorious activity done by any of those 25 people, that will be thrown out and this slashing will be done. Now those 25 people will be given a random time, and then we cannot guarantee that it will be only you or ma'am or sir will be a part of the validator. It could be me, it could be any student. Okay, so that is how we can cater the fairness.
But you see that if you do not have a strong notion of identity, you can, if you are trying to create a different distribution model in POS, what I can do if I see that I am penalized because all the stake is concentrated on me, is I just create a new identity, and then this identity has a higher probability to be selected if it has a lower stake compared to the actual stake that they have. So if you do not have a strong notion of identity, civil protection is difficult. That's why you have civil attacks, is because you do not have strong notions of identity. And I fail to see how this is solved by this, but we can talk about this later.
Sir, yeah, we'll discuss it. Yeah.
Fantastic, thank you.
Thank you, sir.
Yeah, thank you so much. We have really run out of time. So the next speaker will be Professor Samasundra, which will be joined online. So he will talk about the fairness analysis of Hedera.
हेलो लैपटॉप का ऑडियो ऑन करना हेलो लैपटॉप का ऑडियो ऑन करना
Whenever you're ready.
लैपटॉप का ऑडियो ऑन किया क्या हेलो 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 लैपटॉप का ऑडियो ऑन करो
मेरा off है. Sir, can you speak?
Yeah.
Okay,
Can you
good.
hear me?
Yes, yes. You can start.
Can you see the slides?
Yes, we can see. Make it full screen, please. Yeah.
Yeah, thank you. Yeah, here I'm going to, of course, I'm standing between you and lunch. I'll try to highlight what is the challenge in the notion of fairness that has been, even though it was not explicitly defined, how it has been this is something which is completely distinct from the other blockchain systems or the other. So because it is here, right from beginning, you have a global order. So this is something in some sense, once you have a global order, you can have something like a notion of a fairness. Of course, fairness comes into the picture only when you have infinite actions. It's not when you have finite number of actions, there is nothing that comes into the picture. In the just to give a brief rather than going into the detail because the examples may be slightly complicated. Hash graph consensus allows a community of users to agree on the order in which its users have generated transactions even when no single member is trusted by anyone. In a hash graph ledger, any user can create a transaction which will eventually be put into a container, which is technically the block, and then spread throughout the distributed network. One of the distinct features, as I already said, is into the ledger, and none is discarded. That means that whatever transaction goes into the picture, like in the classical other one, the fork is cut, pruned, etc. Here there is nothing that is going to be pruned. That is, all branches are woven together into a single whole tree and continue to exist forever and provides mathematical guarantees with respect to Byzantine agreement and fairness. Now, if you look at the basic hash graph consensus, it is based on the asynchronous Byzantine fault tolerance, wherein honest members of the network are guaranteed to agree on the timing and order of a set of transactions, irrespective of whether some nodes are maliciously trying to prevent that consensus, even if as many as one third of the nodes are trying to negatively affect the consensus by delaying the transactions or otherwise. This could be interpreted as the number of malicious nodes the network can tolerate, but still come to a consensus. Thus, ABFT eliminates assumptions about timing delays, allows some messages to be lost, order or delayed indefinitely. Thus, there is no dependence on the synchronization. So this is a very important thing, how the asynchronous, even though one would say a time how would be defined, this is a different thing which I will not discuss. The only assumption that is made is that at some point in time, messages from an honest node will eventually get through. The eventual delivery of the message makes ABFT more robust and resilient against network latency and other potential disruptions. So essentially what it runs is, the network runs a gossip protocol where each node or peer repeatedly calls other nodes at random, gossiping about the events it has seen till that point. Hash graph is a directed acyclic graph where actual time flows up. It is built on gossip about gossip and virtual voting principles. Actual voting does not place. It computed speculatively, and that's how there is no time that is going to be involved, and also no branch is pruned kind of a thing. It's almost like people who are in distributed computing, people would have understood something like a common knowledge. If you have 100 children and there is a mud on each one, and the person who has the mud on his, he will not see it. And now if you go on repeatedly asking the questions, finally you will know who are all the persons, whether it will converge, who are all the persons who have mud on their head kind of a thing or the other. And so this is a hash graph. The time flows up, and now you can say that now A3 can gossip with C6 to say that what are all the things it has seen. And then, as I said, the direction is up, built on gossip, virtual voting, and no branches pruned kind of a thing. allows the network to process transactions rapidly and efficiently, and performance exceeds that of many traditional blockchain platforms. Like in the beginning, the NPCI also mentioned they had evaluated in the early stages Hedera, offering a reliable and high-speed environment for developers and enterprises to create dApps requiring high throughput and latency. So now the main aspect of this is the global order of transactions. Now here, if you see in the hash graph, there is something like a famous notes. What are all the things, the maximum number of things, what has been seen for the events. I will not go into that detailed definition or the other. So now here one defines how the global order of transaction is defined is the key factor. Suppose you have let X and Y be the events. Let I and I prime be the rounds. That means each round denoted by R in which X and Y are received by the network. As I mentioned, it's an asynchronous round. One message goes to another one. It is shared by two gossip, and T prime be the consecutive timestamps of X and Y. That is the event where X and Y has happened. Note that in asynchrony, there is always a time difference, which is handled through something like a Lampport's time scaling. Random function maps events to the famous nodes as mentioned, kind of a thing or the other. What are all the things that one has made? And so technically it has three elements in a lexicographic order. I is less than I prime. That means that the node, the event, or the events be the rounds may be less, or if the round is same, time is less, t is less than t prime. And if both are true, then you have arbitrary comparison to select unique famous witnesses using the delta. So in other words, what is it you have? You have a lexicographic ordering of three, the rounds, the time, and also the notion of famous stamps. Now the question, what you always have to say that whether this is sufficient, that's what you would see kind of a thing. So now here you have lots of fairness things come into the picture. People have used in the blockchain in a very, not only in Hedera, but in all the other systems. Most commonly used is the classic concurrency. Every request eventually gets a schedule. That means that if I have requested at some point, it gets scheduled kind of a thing. It is never going to be missed. It is called the eventuality. Every request gets scheduled within a bounded time or a number of implementation related messages. You can remember the mutual exclusion problem or the dining philosopher problem. And now the question is, what happens in a Byzantine environment? Now you can define other orders of fairness. If a transaction is sent before a transaction Y, then X should appear before Y in the agreed upon log. Note that X and Y can be sent by different clients, and due to asynchrony, this may not be always possible to do that. And similarly, you have receive order, approximate order, and block order. That means in the same block, the order of the transactions, it does not matter kind of a thing, but this also leads to some other problems or the other. So now here, if you look at it, what happens in Hedera is, now let us compare this comparison with the distributed computing problems. One of the well understood problems that has been done by Michael Rabin at Turing Awardi is the dining philosopher problem. That means that you have a dining philosophers where they share the forks between them, and now they have to be mutually exclusively eating, whether it is possible symmetric. That means you cannot recognize this philosopher is called I, the other philosopher is called J, etc. kind of a thing. You have symmetry and non-determinism. Is it possible to enforce the eventuality kind of a thing? And so by enforcing, but however, when this is not possible in general on a deterministic solution, enforcing a symmetry is possible to achieve starvation freedom, both in the classical DPP. In the classical DPP, each philosopher has only two forks, one on the left and one on the right. The generalized one is a generalized directed graph. On each graph, there is a fork which is shared between a philosopher sitting at the edges kind of a thing or the other. So now here, liveness in Hedera, how is it achieved? By breaking the symmetry through randomization. Because I had the possibility to introduce the famous nodes, I introduced the randomization, I made it as liveness. That means that every transaction is going through, there is nothing that is just pending, it is not wasting its time. But the question is that, is it possible to have starvation freedom? What is the difference between liveness? There is always some action that is going on in the liveness, almost like a deadlock free, but you can see that you can even bound the time, etc. In the starvation freedom, it is not possible. One of the reasons is in the classic DPP problem is possible through multiple transactions. That means that in the classic DPP, both the forks have to be there before it can eat. Whereas in this global order of transactions, each transaction is technically independent, is not dependent on the other. Whereas in the DPP, due to mutual exclusion and others, there are through multiple transactions. Now, that means that in Hedera, all transactions are continuously enabled. That's why enforcing a symmetry is difficult. Rather, it's almost impossible to enforce the eventuality kind of a thing. It is just like a concurrent database transactions. You can choose a set of transactions. If you choose a set of transactions, something else may be disabled, kind of a thing or the other. Now, what is possible without conflict to choose maximally is another question that one has to worry about. And also, now the question is that now that we have a liveness, the question is that whether it is MVB is possible or not. Because there is a starvation freedom, there is a possibility we can look at MVB as a possibility, but it is somewhat difficult or the other. So now to conclude in the discussions, of course, this is a scalable, energy efficient, even election is computed rather than asking the members to do that. There is no pruning, there is no global order, the liveness, but not starvation freedom. And so it is difficult for MVB attacks, but you can't say, prove that there cannot be any MVB attacks. Now the challenge is, in fairness, is it possible to compare the theory versus practice, in the sense that if this one is happening, I can technically consider it as if I have a eventuality condition coming into the picture, and then conflict avoidance of transactions, types of fairness, what is the thing that what one has to pay, can it be handled by different kind of aging and things like that. But one of the most important things is the Hedera uses smart contracts, including Solidity. What would be the interference of Solidity in the context of fairness is a big challenge, because smart contracts introduce concurrency or a distributed concurrency, which could lead to a lot of problems. This is something that has to be tackled in a very formal way. Otherwise, it becomes, while the structure of Hederas shows that we have achieved liveness, and possibly through practice, even the eventuality does not make much difference. But once you introduce smart contracts, it is a challenge that you want to do in languages like Solidity, as compared to what people, NPCI person represented, or even in the Ripple, the way the smart contract is introduced is very at a different stages, rather than through a general smart contract kind of a thing. I will stop here and thank you. Any questions?
Thank you, Professor Samashundra. Is there any questions? Okay. Yeah, Claudio, have one.
Hello, Professor Shamsundar. Thank you very much for this very interesting presentation. I wanted, if you can talk a little bit more about which is the tension that exists between this consensus protocol and MEV, because MEV happens in Ethereum because you can populate the mempool with a lot of transactions, then you need to reorder it. Here, a priori, how is it that you see potential for MEV happening?
No, one of the reasons the MVV can happen is that you have to constrain yourself to say that there are some transactions that are never going to happen. It is something like a conspiracy that happens in a dining philosopher problem. By telepathy, if two persons join hands to see that in between fourth cannot be shared by the other, this transaction will ever be starved. And so that means that this man can never get executed, and that way I can get a MGB done, kind of a thing out there.
Thank you so much. We have a bit time for one more questions if you. Okay. Otherwise, okay. Thank you so much, Professor Samasundra.
Thank you.
The next speaker will be Tao Yang.
Yes, I'm here.
Okay, we can hear you. So when you're ready, you can start your presentations, right?
I'm going to share my slides. Give me a second.
We still cannot see your slides now.
Yes.
Not yet. Okay. Yeah. Thank you.
Can you see my slide now?
Yes, we can see that.
Okay, perfect. Now I'm going to start. Hello, everyone. I'm Tao Yang. Today I'm going to present our recent research, which is from MEV rewards to the consensus security, tracing MEV payment flows in proof of stake Ethereum. Start from some background information. And this MEV problem comes from the issue of mempool on Ethereum. As you may know, transactions in the mempool of Ethereum, they are publicly accessible. Users can monitor this mempool and also view the details of this transaction. And this creates the opportunity for the malicious users, and they can identify these profitable transactions. And then they just pay more gas fee to let their transaction to be executed firstly before others' transaction. This is called front run in Ethereum. And now there are many bots, they are monitoring these mempools, so to find such opportunities. And here comes the concept of MEV. MEV, the full name is maximum extractable value, which refers to the block producers. It is miners in proof of work Ethereum, and the validators in proof of stake Ethereum. And these block producers, they want to maximize their profit from users by ordering transactions in a block. And the MEV activities include front running, back running, sandwich, arbitrage, and liquidations, etc. In the context of proof of stake Ethereum, originally validators will build and propose blocks, and this caused potential risks. Firstly, validators will have the incentives to destabilize consensus to capture MEV, because this can bring the extra profit revenue for the validators. Secondly, and the professional block builders like Lido, these very large players, they will have higher computing power than the solo stakers, and they can build these blocks more efficiently, and this will also make coarse the concentration of the staking entities. To solve the problem of this MEV, the proposer builder separation is introduced to reduce this problem. And what is the PBS and MEV boost? The proposer builder separation splits validators duties between the builder and the proposer. Right from the left plot, the validators, it has two rules before. Now, the builders will just build the block, and they will send the blocks they built to the proposers. And the task of the proposer is very easy. They just choose the maximum profit block, and then they publish this block to the network. And to do this, proposers need to run a middleware, which is called MEV boost. So MEV boost, it is an implementation of PBS. By doing this, proposers will not control the order of transactions in a block, and they will just select a block and propose this block to the network. In this, our research, the objective is to understand the mechanism of MEV boost and the function of each rule, and we also want to identify the MEV payments between different rules, and we want to see how concentrated is the MEV market across different players. This slide, we want to just explain a bit about the different rules in the MEV boost. So here we have, first you have the searchers who are going to identify these MEV opportunities through public mempool and also through the private channel. And they are going to identify these MEV opportunities, and they will build the block and send to the builders. Sorry, the searchers will only send to these transactions to the builders, and the builders will start to build the block through the public mempool and also from the private water flow. They will try to maximize the profit in a block, and then they will send the block to the renays. And the renays here is very important. It will rename the blocks to the proposers. In the meantime, they will keep the MEV, these transactions, as a keep it as a secret. Only after the proposers signed the header and return this header back, the rename will publish like the blocks in full to the proposers. And finally, the proposer will propose the block, and these transactions, these MEV transactions are confirmed on the blockchain. And there are several payments in the entire process, such as the payment from the searchers to builders, and the payment from builders to the proposers, and also the payment from builders to searchers. But in our research, we just focus on the payment from builders to the proposers. And there are 4 ways for the builders to make a payment to the proposers. The first is a direct external payment. The builder sets its own address as a block miner address and sends a last transaction in the block to the proposer's address. A second way is a payment from another builder address and to the proposer's address. The third way is to indirect payment via intermediate address. So the builder send the payment to an immediate middle address, and this middle address will finally send this payment to the proposer's address. The last way is to direct coin-based payment. The builder sets the proposer's fee recipient address as the miner's address, and finally the proposer will receive the payment directly from the transaction phase and the block reward. In our research, we captured the data from the part 1 and part 3. The data is collected from Duan, so we construct the data set from the Ethereum external transactions, internal transactions, and also internal transactions, and also some label data on Duan. And the time framework data is from September 1st of 2023 to September 13th of 2025. How we identify the MEV boost blocks is the first question when we start our project. And there is a PBS convention. There are some rules set by the PBS, which is that in the MEV boost, a builder will set its address as a fee recipient address. And then the builder will pay the proposer in the last transaction or block. And we are going to identify the last transaction of the block and check whether its front address matches the minor address of this block. If it is, the block can be considered as MEV boost block, and the Ether amount of this last transaction is considered as a payment from builder to the proposer. By collecting this data, when we are able to calculate the payment and the profits of different players, the searchers, builders, and the proposers by following these formulas. Basically, the searcher payment equals the transaction fee plus the searcher tips, which is Ether transferred directly in the last transaction of a block. And the builder revenue equals the searcher tips and plus the gas fee and also the a gas fee paid by non-searchers. And the proposer profit equals the builder payment plus the block reward from Ethereum. But here we didn't consider the block reward because it is paid by the system, not by the users. Here we are going to demonstrate some our results. Firstly, from this time frame, this time range, we found the MEV boost dominates the block production on Ethereum. So if you can see from the plot, the red, no, it's the blue part. Yeah, they account for about 90% by August 2025. So the MEV boost blocks, they account for the most share of the block production. And this plot, we want to show which is the main payment, which is the main way for the builder to pay the proposer. There are two ways. They are going to set a high gas fee, and or they are going to pay to the proposer by a direct Ether transfer. From the plot, the main way for builder to do this is to pay by a search tip, which is in the green. And then we want to check how these profits are distributed among builders and proposers. And from this plot, we can see most of our profits, around 70% to 85%, went to the proposers. Furthermore, we want to understand the market structure of the builders market and the proposers market. And here we can see some main players of the builders, such as Titan Builder and BV Builder. They account for most of the profit of the builders. And this, there is a similar situation in the proposer market. Entities like Lidos, Coinbase, they also account for 80% of the profit in total. And then we calculate the HHI index and the entropy and the Gini index as well. And all these measurements show that the builder and proposers, they have concentrated profit distributions. As we find this contribution pattern, and we further check if there are some combinations of these players. So from this Sankey plot, we find a small set of searcher, builder, proposer routes account for most of the total MEV transferred. And from this heat map, we can also identify some builder searcher peers and also the builder proposer peers. For example, the Titan build and with this address, and they has a lot of these order flows. And also Titan build and also the Lido, they also have a large amount of this order flow. To conclude this research, so here I firstly want to mention like how this concentration of MEV will affect the security of Ethereum. Firstly, if it firstly comes to the transaction censorship, the builder market is highly concentrated. These top builders, they have the power to determine which transactions can be selected and will be recorded, will be executed on the blockchain. And secondly, the proposers, they may will play the waiting games. So a proposer is intended to propose a block on time, but if they have this MEV, they may wait for the block which has more MEV profits, and this may delay the consensus process of the Ethereum. And finally, it also may cause the validator concentration, because MEV profits currently are also concentrated in a small number of proposer entities such as Nido and other solo stakers. They cannot receive a lot of MEV profits, and this will decrease their incentives to stay in the system. The last thing I want to mention is that MEV Boost was designed to decentralize proposers, but unfortunately, it also caused centralization in the process. So to solving this paradox is a key challenging and is very important for the Ethereum development. Thanks for your attention. Do you have any questions?
Thank you so much for the nice talks. Yeah. Is there any questions? We can have one. Okay. If not, so thanks all the speakers one more time. I think you have announcements about lunch.
Yeah, so we can break now for lunch, and we will reconvene around 2 o'clock, exactly 2 o'clock. So lunch is at the back side of this auditorium.
Good afternoon, everyone. I'm Parminder Kaur from University of Zurich, and today I'll be sharing the afternoon session, so please don't fall asleep. So for the first session, I would like to invite Abhijit Chakraborty from IISER Tirupati. Is he here? Abhijit Chakraborty will be giving his talk on evolution of the Bitcoin networks in collaboration with Professor Yuichi Ikeda.
Welcome back everyone after lunch. Probably you will be feeling sleepy. I hope I will not help you in that much. So I'll try to keep my talk as simple as possible. So today here we are starting the evolution of the Bitcoin networks, particularly the networks of user. Probably many of us have the notion that the transaction in blockchains are anonymized. But that is not true. If you do little bit of statistical analysis, you can identify the user. And here we will be studying about the evolution of networks, like we will be constructing the networks of user extracted from Bitcoin transactions and how it evolves over time. So particularly our scale will be weekly windows, and we'll check how the complex network changes over time. So first thing first, the data. So the data we have collected from the Bitcoin blockchain, starting from the Genesis block to the block height of around 700,000. That corresponds to the time step around August 2021. So this is the block time, and we have every block have collect the transactions. So when I talk about a time step, so generally the transactions are written within the block within around 20 minutes. So whenever I talk about time, so please consider it as an accuracy of 1 hour. So this is the accuracy of hour. So and typical transaction in the data contains multiple input and multiple output addresses. That is the public key. And we extracted pairwise transaction between users. So how we extracted the transaction between the users, I am going to explain that in the next slide. So generally this is the typical transaction. Let's say the transaction 1. So let's say this address A1 and A2. These are two input addresses which sends like let's say those are addresses of the Alice who transferred 1 Bitcoin to Bob, who has Bob has address A4, and A1 is output again Alice address. So this is because Alice uses two address, because one address doesn't have the enough balance to 1 BTC. So that's why Alice needs two addresses as an input to send the $1 to Bob, and the change is returned again by the address A1. So this is the first transaction. In transaction 2, let's say another day Alice did another transaction to Carol. Then she uses A1 and A4 to send it to Carol address A5. So where A1 and A4 are Alice address. So from this data we can identify the address of A1, A2, A3 belong to Alice. Although A4 and A2 doesn't appear together, but we can say that that will be A3, A4, A1, A2, A4 belongs to Alice, not A3. So there is a mistake. So A1, A2 and A4 belongs to Alice. Although A2 and A4 do not appear simultaneously, but we can identify that is a Alice address. Okay, so we can identify that A1, A2 as Alice address. So for a large data, you can just make a undirected network between the input addresses, and then you can look at the different connected component, and each component will be a address of a user. So in this way, you can identify the users, and then considering this subset of user, you can make a users as the node of the network, and if there is a transaction between users, you can make a link between them. So this is required looking at the transaction in the history to identify many addresses with the users. So this is the daily number of pairwise Bitcoin transactions between the users. So where you can see this is not the total transaction. This is a subset of transaction because we are using now the transaction between users. So this is a daily transactions, whereas the right hand side gives you the transaction amount in terms of Bitcoin values. So and I have considered the period from 1 year period around, so July 2020 to August 2021. So why do I choose this year? So there is nothing special about it, but this is just a preliminary analysis. So it covers this peak around 2021. So our initial idea to check how the network evolves around these peaks. So this peak, around this peak, there was a kind of a fluctuation of this price. The surge in Bitcoin price was like 2000% in a month, and subsequently it has decreased. It was decreased by 64%. So you can imagine that such kind of return you will not get in any other financial asset. So the Bitcoin is special, and so that's why I attract it to the investor and as well as to the researchers to having this kind of volatility in the Bitcoin. And that's why we are interested in studying Bitcoin networks. So we constructed the weekly Bitcoin networks of users, so where the nodes are the users, and so please note that these are users, not the addresses, and they do at least one transaction in the on that particular week to be a part of the weekly network, and links are weighted directed in nature, and weight represent the daily amount of Bitcoin flow from source user to the destination users. So this is the number of nodes changes in the weekly network together with the Bitcoin price, which is shown in this blue triangle. So you can see that there is a increase in the number of nodes in the weekly networks towards before the price surges. So we can say that when the Bitcoin price was increasing, more users were doing transactions, so there was an increase in the number of nodes. But as subsequently price falls, we also see that there is a less interest from the user to do transactional activities. And this is the number of links per node, or you can think about it as an average in degree or out degree in terms of network language. So this is we can see that the degree average degree is around 1.8, so it varies from 1.95 to 1.75. So it shows that the network is very sparse. So there is not much loop in the network. So it shows a very kind of sparsy nature of the network. And these are the number of total weight varies in the weekly network. Sorry, I wrote it daily, but it's a weekly network. Yeah, so this is the kind of the variation of total nodes. So these are some of the network statistics. Generally, the network scientists do this kind of statistic to understand the structural properties of the network. So this is in degree distributions of the network. In degree means how many incoming transactions one user gets. So this is more like a heavy tail nature, and it could be fitted with a power law. This rank size distributions of in degree, and so we can see that all sizes exist in the in degree distributions. And next I will show you the out degree distribution, which is you will see there is slightly difference in degree and out degree distributions. In out degree distributions, we have a heavy tail nature, but there is a hump you can see around the values between 10 and 100 in these two periods. So these are two different weeks. So one is around 2020 and another is 2021. So this is 2020 is I choose this week because that time there was price is quite stable, and this March 1 and 7 there was a kind of very high volatility in the Bitcoin price, and so we can see that's why the humps actually shifted slightly right side here. And what is the meaning of this hump? So it may be related to like so out degree probably represent you rely how many with whom you want to do transactions. So it's like you rely those destinations wallet destination users. So it's more like in social physics. So there is something called Dunbar number. So how many of you can maintain social relationship among in a society like your friends? So you can maintain probably in according to Dunbar number it is 150, but we can see probably it might be related to that. We can actually do normal users can actually do a certain limited number of transactions with certain limited number of users. So which could be between 10 and 100. So this might be related to that fact, and towards the tail these are probably the user which are having some kind of commercial interest. So they do lot of transactions, so they do not follow those kind of Dunbar number in as the normal user do. So we can clearly see there is a deviation between these two type of user. Although we have not actually gone through it details, so it's just a preliminary study. We need to investigate more details on this. So next is I looked into the bow tie structure. Generally any directed weighted network could be decomposed into three component, mainly three component: in component, GSCC component, and the out component. So first what we do is like you map the network as a unweighted and undirected network. Then you look at the what is the size of the largest component, and then that largest you take the largest component and then you decompose that component into considering the directed nature of the link in component and giant strongly connected component and the out component. So in component are those nodes which having a path from them to the giant weakly connected component, and from out component are those which having a path from nodes in the giant connected component to them. And giant strongly connected components are the nodes, they have a mutual path between any two nodes. So this was actually studied long ago into 2000 by on a wave graph. So this was done by Border and his co-authors. Like they have taken a massive wave graph on wave graph from crawling Alta Vista. So if you may be familiar with the search engine Alta Vista, which was before Google. So it was very popular search engine at that time, and they had two crawls from this Alta Vista, and they crawled like around 200 million web pages and 1.5 billion links. So from them they have extracted, they found that this web directed web graph has this kind of bow tie structure. So it has a central core and two wings. And they found that the in component, out component, and core has more or less similar in size. And due to the shape, they name it as a bow tie structure, and it's famous in network science framework. So we looked into that, and we find that the number of nodes in the largest connected component, and so this is the number of nodes in the largest connected component of the Bitcoin weekly networks. And we can see that the number of nodes is actually more than 90% of the total nodes in the weekly Bitcoin network. So the network is more or less connected. And these are the number of nodes in different bow tie components. So we looked into the how many nodes are in the in component or out component or GSCC, or the rest as the tendril. So these four are represented. So black represents this GSCC, giant strongly connected component, whereas the red represents the out components, and blue is the in component, and magenta is the rest of the node, that is the tendril. So you can see there is a crossover here where the out component actually increases from the GSCC. So it's become that you have a more large out core out component than the GSCC. So this is actually happening during the price search, when we observe the price search during the 2021. So this might be related to that, and we can see that there is probably a structural change in the network during that time. So that was the number of nodes in absolute term. We also looked into if you look in the fraction of node in each component, so which looks like this. So this is the same plot, but I just showed you in terms of fractional number of fractional nodes. We also looked at the distance, the number of how many steps away these in-out nodes from the giant strongly connected component. So we found that the number of the maximum distance from the nodes from the GSCC for the out component could be around 250, and for the in component it could be sometimes around 100. So this shows that the network is some of the nodes are not well connected. So this might be against this small world nature of the network. So it's more like very sparse, and most of the nodes are not well connected to the core of the network. So this is another one our finding. So to conclude, we have analyzed the Bitcoin data using directed weighted network, and we have shown that temporal evolution of weekly Bitcoin networks of users, evolution of Bitcoin users, and particularly we explored the evolution of bow tie structure. So we have some future directions. So this is a very preliminary study, and we wanted to extend it for more recent years, but we have not done so yet. And we also would like to study some Bitcoin user network spectra, so which I have studied in the past. Like we have uses this time series data, and this time series data, and we have embedded this time series data to using network embedding, namely node-to-vec algorithm. And you can convert the network nodes into a nodal vector. So so this is one of the example how to embed. So so this is where you keep some structural property as a intact, like the community structure of the network, and then you can convert it into network. So this is the network embedding part, and then after we get the node vector, you can calculate simply the Pearson correlation between the component of these node vectors. So you can choose a dimension, and you can calculate the Pearson correlation and tensor about it. And once you get, so this will be a correlation correlation tensor, not a matrix. So we have to do kind of do a dimensionality reduction. You have to do singular value decomposition, but you have to do it 2 times since it's a tensor, not a matrix. So we have done that for not for Bitcoin, but we have done it for XRP. So this is in this way you can just do a singular value decomposition of this tensor, and you can look into the singular values or the spectra of the graph, and this can be related to the price of the crypto assets. So this is the method we can do it. So this is we have done it for XRP transaction network. So this gives the spectra for the black dots represent the spectra for the empirical network, whereas this green and the triangle is given for the red triangles are for the randomized network, which could be used as a reference how it's different from the random data. So we would like to extend this our work in this direction. So with that, I will end my talk here. Thank you very much. In case if you have any questions.
Thank you very much, Abhijit. It was a nice talk. Do we have any questions?
Thank you for the presentation. I had a question, 2 questions actually. The first one is related to the bow tie structure. Did you randomize the network to see how relevant are these in, out, and SC components?
Yeah, I tried to do the randomizations, but we cannot do like a strict randomization. So this is a directed network. So and a very sparse. So if we do like a very strict randomization, it would be difficult, like preserving the in degree and out degree as a constant. So that cannot be done. But there we can relax this condition and can do that. So that I have not done yet.
Okay. Could you please? There was another question that I had related to the out degrees that you had before this. There was. Yes, this is a Dunbar number that you had in your data. Because I understand in a social network context the existence of the concept. The problem that there social ties are each one of them absorb some cognitive capacity of the users. Here actually there is something that is important, I think, which is the wealth that you have, because this is also something that determines how many transactions can you make. Did you make any analysis of how is it that the out degree depends on the wealth of the participants when they are performing the transactions?
No, that I have not done. Yeah, that's a good suggestion.
Thank you.
Thank you.
Okay, let's thank the speaker again. Thank you. For the next talk, I would like to invite Matija Piskorek from University of Zurich and Ruther Boskovic Institute.
But I think it's not, I think it doesn't work. So, no, that one is mine. We can just try some other one. Okay, this one works, great. Otherwise I would, the laptop would not make it. Yeah, and
Matija will be speaking on rewiring core persistent batch periphery, evidence of Sybil coordination in Monero.
Great. Hi everyone again. So this is, again, I'm Matija Piskorec from the Ruđer Bošković Institute, and also from University of Zurich. I'm working together with Claudio and Tessone. This is a paper that we did together with Yu Gao. She's a PhD student in Professor Tessone's group. And this is an ongoing effort where we're trying to map the peer-to-peer network structures across various blockchains. This work, we will describe some preliminary experiments that we have regarding something that we observed in the Monero network. We've been working on the Monero peer-to-peer network for some time because, as you know, peer-to-peer protocols, the first one was in Bitcoin, and then most of these other protocols, they inherited peer-to-peer from Bitcoin. For example, Litecoin, Dogecoin, and so. But over time, they introduced some changes. And Monero is just one of the iterations, one of the forks from Bitcoin. One of the main things is how nodes can maintain consensus is they have to communicate somehow. And they communicate through the peer-to-peer network. And peer-to-peer means that there is no centralized repositories of which nodes are present in the network. So there is a bit, okay, I can always come closer. So in Monero, there are these two lists called the white list and the gray list. White list is basically a list of all the IP addresses that the node saw in some recent time, while the gray list is anything that doesn't fit into the white list and all the IP addresses which didn't respond to the node, which didn't communicate with the node for some time. So these two lists are maintained by every node. There was this work by the people from Hong Kong a couple of years back where they tried to do the same thing to infer the peer-to-peer network in Monero. And I can assure you that blockchain community is, especially from the protocols which are privacy-oriented, such as Monero, they are following closely all the academic research that's being doing. And for example, after this one, they did some changes to the protocol. So after the Hong Kong group. So in particular, there was this additional piece of information called basically you could know for every IP address when was it last time seen in the network. And after this work was published, they basically removed it from the code because they realized that it doesn't enhance the peer-to-peer protocol, and the sole fact that you can infer the peer-to-peer network partially de-anonymizes the network, because if you know which nodes are connected to whom, you can, for example, try to infer from which IP address did the transaction came from. So our work is basically built on top of that. We tried to infer peer-to-peer connections without relying on this last seen timestamp data. So we set up our own data collection pipeline. We had 3 geographically distributed nodes, one in EU, one in Singapore, and one in the US. And we did monitor their TCP traffic. Because these peer lists are not exposed in the node interface. So if you want to get them, the only way you can get them is by just monitoring the traffic. And we did collection for more than half a year. The idea is that although these lists, there are certain rules how these lists get updated and you do not get information who is connected to whom at what particular time. But what you do get is kind of you can be sure that if a certain IP address appears many times in the list, then it's more probable that this is an active peer and an active connection of a certain node. So this is an underlying assumption. So it should be possible to distinguish active connections based using only frequency analysis just by looking at the IP addresses which appear in these lists. And these are some of the results from the paper that we published in ICBC last year. Actually, it was this year, where we reached certain level of accuracy, not to the level of the Hong Kong group, but we basically had to work with less data. But to some extent, it is possible to reconstruct the peer-to-peer network. So this was our, so this is, for example, how peer-to-peer network looks like. Actually, one small part, it's not a small part of it, but a small part of it is highlighted. And here we highlight the between centrality and the degree of the node. What you can see here is that there is a core of densely connected nodes, which we call the supernodes, which are almost fully connected. So this means that they maintain connections between each other. And this is a feature which we noticed being consistent over time. So ever since the beginning of our data collection period, these supernodes are more or less stable. This in itself is a problem which I will actually maybe not tackle that much here, but when we talk about decentralization, we can talk about decentralization on various levels, and peer-to-peer decentralization is certainly one level. The other level can be on the level of value, the account balances, service providers. There are many different levels of decentralization. This is one of them. If you compare the way how Bitcoin is managing the peer lists, again, it has these 2 lists. One list is for all the nodes that it's tried to connect and all the nodes that it found and are the new ones. Monero has this white and gray list, which is a bit different. And our current work was inspired by the work on eclipse attacks in Bitcoin. So eclipse attack is basically a way to isolate the node by dominating the node's connections. So there are various ways how you can perform eclipse attacks. You can do it on individual users, individual nodes, miners. It always involves, let's say it's a form of a denial of service attack in the form, not maybe in the form of denying the service, but dominating the connections of the node in a way that the node basically has a very skewed view of the network. So this has been shown in this paper. eclipse attacks on the Bitcoin's peer-to-peer network. So it is known for some time, for at least 10 years, that these kinds of attacks are possible. So if you're following what's happening with Monero recently, it was quite a news during summer. There was actually a 51% attack on Monero. So 51% attack means that in the proof of work, also in the proof of stake, basically if you control 51% of the resource, either being the stake or in case of Monero and Bitcoin, these are the hash power, basically you can dominate the network, you can take over the network. And 51% attacks, they are very rare. They don't happen often, especially not for the big blockchains. And actually this summer, this happened with Monero. It was an attack by a mining pool called Cubic. And they didn't do, let's say they didn't do it out of purely malicious intent. They actually have a plan out of it. They have a plan of taking over the Monero network with the 51% attack. Because they're a mining pool, they can actually afford to do it. And then when you take over the network, you take over the consensus, and basically you don't have to spend rest of the hash power for hashing. You can spend the rest of the computational power for whatever you want. So they published their own token, and they wanted to make. They have this idea of overtaking proof of work blockchains is actually beneficial for their society, but this is maybe a story for some other time. The fact is that the Monero was in a way overtaken with this 51% attack. Because we were already collecting peer-to-peer network, we actually wanted to see, can we see this overtake in the peer-to-peer network as well? As we were continuously collecting the data, we also collected the data before and after the Monero takeover. The thing is, if you have 51% of the hash power, you can basically dominate the consensus. But there is another way of dominating consensus, is by dominating a peer-to-peer network in a way. So with a form of an eclipse attack. So if you have enough nodes, you can try to dominate the network by overtaking the connections of different nodes. So we wanted to see whether, by analyzing peer-to-peer network, we can actually see whether there is any evidence in data. This is how the network visualization looks like. On the left, it is a state before the attack, and on the right, it's the state after the attack. It's maybe not plain, maybe you cannot see it from here, but I can explain. So the set of supernodes basically changed. Out of previous 14 supernodes, now only one of the original supernodes was here. So this indicates a pronounced and sudden core level structural shift. The other thing that we monitored is there are these, because we have the IP addresses of the nodes, and some of these addresses have the same prefixes. And if you know from how networking in the Internet Protocol works, is if you have the same prefix, there's a high probability that you come from the same service provider. So maybe you're a member of the same university network, AWS service provider, whatever. So we were also investigating these batches because it is known in Monero that sometimes there are some malicious nodes which are actually not full nodes, but they work as proxy nodes, and they all have these very similar prefixes, which means that they come from the same network. And we do identify a couple of clusters of these prefixes. This for us is an indication that there is potentially partially coordinated Sybil-like occupation, what we call of the periphery. So these supernodes, they don't come from the same, they don't have the same prefix, but the nodes that are surrounding them have the same prefix. So the idea is that maybe some of these nodes are, in a way, not performing an eclipse attack on purpose, but maybe it's kind of the structure of the network that these supernodes are actually seeing what their periphery is telling them. So this is, let's say, still preliminary work. but it gives us some conclusions. So first of all, we saw this restructuring of the core, where the set of the core nodes completely changed, and second, we hypothesized that potentially there was some Sybil coordination in here as well, because of these suspicious batches of prefixes persisted. So this is it. Thanks.
Thank you very much, Mattia. Do we have any questions?
Mm-hmm.
Understand. So let's take the first tuple. Okay, so the prefix is 142.
So if you're talking about tuples, the rows are not connected.
Not
it's
connected.
yeah.
So somewhere like 209 corresponds to second tuple, like that.
It's
no relation.
no link. Yeah, these are just three separate columns.
So what do we mean by prefix?
So prefix is so if you see the third column, the prefix means that this last number in the IP address can have one of the 256 values. So on the last column, the first one is 142.27x. So if you observe IP addresses coming from this with this specific prefix, this means that they're in a network sense, they're somehow connected.
You mean these many entries have at least 60 repetitions of IP address?
Yeah.
Only the last position.
Yeah.
is
Yeah.
different.
Yeah.
I do not have a question, I only have a comment, and not to sound pedantic, Mattia, don't get me wrong. But the story of Cubic is slightly different, and I think that it brings value actually to why it happened actually. Cubic is actually another blockchain that has programmable proof of work. So through a decision-making process, they decide what do they want to do with the computing power. And actually what they decided to do, now following your logic, is decide to start to take over smaller proof of work based blockchains, because they had enough computational power. So what they did as a proof of concept was, okay, now while you are mining Cubic, and this is the logic, while you are mining Cubic, at the same time you are also mining Monero. Then later attacked Dogecoin and others, because they can decide what they want to program. And actually this is why they were able to take over Monero for actually not only these weeks, but eventually for a month afterwards.
Yeah, you actually explain it much better than me. So from the Cubic standpoint, they are adding value to the system because they are doing useful proof of work.
Exactly.
From the Monero community standpoint, they are malicious attackers.
Exactly, that's the point, absolutely, fully agree. And the point is, actually, from the economic point of view, Cubic is a rational decision, because they are mining two tokens at the same time. They are mining the Monero and also the Cubic one, so they receive twice the rewards for the same process.
The only collateral damage is the decentralization in Monero network, potentially. But yeah.
Thank you.
Thanks.
Thank you, Mattia. Let's thank the speaker. Now I'd like to invite the next speaker, Krongtum Sanketwang from Kyoto University. He'll be talking about closed work dynamics in weekly crypto asset transactions, graphs, and their relation to price.
Okay. Hi. So today I will present a preliminary result on using on-chain data to determine the closed walk dynamic on weekly crypto asset transaction based on the graphs and their relations to the price. So first, making some more motivations. So a lot of studies have been found that during the price fluctuations, there are a lot of correlations in the increases of anomalous activities, for example, and this can be somehow seen in terms of the patterns that can be detected. For example, in the left-hand side, you can decompose the flow from one address to another address to be into two components. The one is the direct flow is called like potential flow, and the other one that measured the circulative transactions that can be looped flow. And then you can see from the plot that basically that during the price search period, the changing in the loop flow and the potential flow can be found. And also in another study that I have been a part of, where you plot out the scores, over here is C-scores, that basically tells you how the topological change in terms of the structures of the graph, of the weekly transaction graphs, is behave compared to the price search is plotted here. So, for example, you have the kind of like this pattern versus like the patterns where you have the circulative motions of the flow of the crypto asset like this, and then you can see that during the price search in the red lines here, these types of patterns have been found to be increases rather compared to this one is decrease. So with that in mind, my goal of the studies preliminarily is to characterize the market behavior during the different market conditions, and that it comes to the concepts of like how we actually characterize it. So I use the concept of the closed walk, which is quite related to something called like first Betty number. For example, if you have on the left-hand side here 4 nodes, you can think about 4 users, A, B, C, and D. A sent maybe Bitcoins to B, B sent a Bitcoin to C, and C sent another 2 Bitcoin to A and D, and then D sent back to A. So basically, this sequential transactions where the funds return back to the originals is called the closed walk concept. So what how can you actually detect this closed walk? You can basically, for each particular graph, you can have a matrix that basically tells you how each node is related, how each node is interacted, basically. For example, this matrix called adjacency matrix A, right? So I wrote here adjacency matrix A of this particular graph. So you can see that each row represents each node, right? The first row is the node A. Node A interact with B. This one, node B interact with C. This one, node C interact with A and D, and so on. And the way that you count the numbers of closed walk is to sum up the diagonal line of this matrix, right? So you can count the number of walk with the length k by doing the metric multiplications. For example, the trace of A, it's a self loop. The trace of A to the power 2 is numbers of walks with length 2. The A to the power 3 is length 3, for example. When you count this one, you have 1, which is basically from B to C and back to A, and then so on. So this, with this in mind, you can directly measure how many circle or how many self loops that exist in a particular graphs. And also, you can somehow estimate them using this Hutchison's stochastic trace estimator. But previously, what you wanted to do, you wanted to calculate the trace of A to the power k, right? So now you also want to do the same thing, but just imagine that you cannot do it directly because of your A is maybe too huge. What you can do these tricks where you draw the C. Basically, C is kind of random vectors where they have the mean
of 0 and variance is 1. And basically you can just take the expectation value of these expressions, and then what you get is a trace of A. So I have an example of 2 by 2 matrix here. So basically what you have is the trace of B, it's equal 5. And if you want to estimate it using the random vector Z, you can simply write it exactly as what the expressions here is look like. So you have C1, C2 with A, and the first one is the transport, the second is the vector, and then you write down, do the multiplications, you get these expressions, and then you take the expectation value, where you know that the mean of this Z is 0, variance is 1, and what you get is the trace B equal 5. So you can use these tricks to somehow getting for the biggest A. So now previously you have just A, right? Previously you have just A. Now you can do with A to the power K, where you repeated this process of Z transport BZ many times as you want. So what you get is basically the estimations of the trace of K. But now, what you have to do is you have to carefully choose the sample size of your random vector C is based on this S. It's basically, this is the number of how many random vector you want to generate it. And study scopes of my talk today will be just in this to highlight periods. I will study 3 types of crypto assets, the Ether, XRP, and Bitcoins. And the aims of study is to determine how many numbers of close walk is existed between 2 periods of the study. It's the one where you can see that the price is rather fluctuated, and the one with the more quiet period in terms of the price. And then this one, I show you the exact solutions from the concept of A to the power K without estimations. And then you can see that for the Ether one, with the first period where the price is fluctuated, you can see that the numbers of crosswalk somehow increases as a shadow of the price, right? And then you can see over here, I plot the numbers of close walk of length 2 to length 6, right? And then you can see that afterwards, when the price is collected, the numbers of the close walk subsequently declined. And then after the price search period, you have the quiet period where most of the numbers of close walks is rather flat. And then you can see that it's starting to get higher at the last period of the study, because of if you take a look at the price, it is getting building up to the next price search. And then for the XRP, you see the same. You see the same patterns where when the price increases or the numbers of close walks, it increases. And when the price is quiet period, you see that the numbers of close walks is rather stable. But the next question is, how about the Bitcoins one? The problem of Bitcoin that I cannot get the direct solutions is because of numbers of address in the Bitcoins. Basically, the numbers of transactions is very huge. And the problem is, like, when you want to calculate the trace of A to the power K, you have to do multiple times, like K times of the metric multiplications. Basically, you want to do it A to the power K, right? So basically, within the setup of normal PC, or even like in some of the high-speed computers, this one will be quite computationally expensive because of it consumes a lot of energy. You have to store at least two adjacency metric, A to the power K minus 1. Basically, it's the previous calculation, and the A, because if you want to do the A to the power K. So this one, it's impossible in terms of the memory management. So of course, we want to use the estimator. So what I show you here is the estimations based on the numbers of nodes. So basically, this is the size of the graph. I have 10K, 20K, 30K, and roughly like 50K size of the nodes. And what I plotted here is the solutions, like the estimations of trace of A to the power K. So numbers of close walk, of the length 2 to 6. And then I have the actual solutions, which is the dot red line here. And then I changed the numbers of sample size, if you can still remember, that the numbers of sample size S here is how many random vectors you want to generate it, right? So basically, in theory, the more is the better, but you have to trade off because of the more random vector you generated, the more memory is consumed. So you have to choose quite nicely what it's the good estimations, right? So over here I varied the numbers of sample from 10, 100, 1,000, and 10,000, and then you can see like just only 10,000, it can give you with the error bar is very small. It's almost close to the actual solutions. So over here you can see like the sample size around like 10,000 up to 100,000 should be enough to get like acceptable accuracy for the estimations. So what I plotted here is the comparison between the actual one and the estimator of the XRP, and then you can see the agreements between these two. It's quite good. And then I show you the differences for the comparisons, where I put the actual numbers of the close walk of the length k, the difference with the estimations. And then you can see that the fluctuations is around just like 0.1, right? And then when you plot out the CPU time use here, with the functions of number of nodes, like basically how large the system size is, you can see that if the node size is very small, the direct calculation will be more profit. But when you go with the larger systems, when you go with the larger systems, you will see that the direct translation, the direct calculations will be much costly compared to the estimator one. And then this one I also plot out the result of the ether. Same picture, you can see that the difference is very small. And over here, because of the system size, it's larger than the XRP, you will see that the differences between the estimation one and the actual calculations is more pronounced, where you can see clearly that when the system size is very small, you won't get any benefit from the estimation. But once you go very further on the larger system size, you will have benefit of the calculations from the estimation, roughly like 1 order of magnitude. And then come to the key of why I wanted to use the estimator is basically Bitcoins. Over here, I can just only do the actual calculation for the Bitcoins up to the length 3, right? It's a to the power 3. The other ones, I cannot do it with the actual calculation, so I plot out, just only the estimations. And then you can see for both length 2 or length 3, the difference is rather small, like 0.05. And then you can see that the clear patterns where the price increases, the numbers of circle, close walk in this sense, is increases. And then when the price is collected, the numbers of close walk is subside. So I also plot out the CPU times, and then you can see like over here it can go up to like 1 million nodes, which is actually impossible for the direct calculations to do that, but for the estimator it's doable. So with the conclusions in 3, what's it called? in 3 categories. The first one will be like the market anomaly detections. So the numbers of close walk effectively characterize the market behavior. It's acting as a proxy for a potential circulation trading patterns. And then we can observe the sharp peak when the price is increases of all like XRP, Ether, and Bitcoins. And for the methodological contributions, here we found that the direct metric multiplication is computationally inaccessible for a very big system size like Bitcoin, 1 million nodes, but the estimator can successfully perform the task. And we found that the estimator show very high accuracy compared to the direct translations, and then we successfully perform the calculation for the Bitcoins. So thank you. Any questions?
Thank you.
Thank you for the talk. I just have a question, like how the number of closed work depends on the number of nodes in the network.
The numbers of closed walk actually is not the functions of the numbers of nodes. It's
Just how does
here, right?
No,
You mean something like
just
that.
the number of your number of closed work.
Yes.
Here, how does it your y-axis depend on n number of nodes?
And numbers of actually, I wouldn't say it's like linearly directed. I've never checked it, but I suppose when you have the higher numbers of nodes, when you calculate the numbers of walks, of course, you will have higher numbers of closed walks. Because of when you have the adjacency matrix, right, and then you do mathematic multiplications, of course, you will, when you go up to maybe like powers 5, 6, the numbers of the diagonal line will be higher compared to the smaller system size.
Yeah, so my suggestion would be to take the system size effect in this
Right.
calculation in consideration. So
Yeah, somehow it's indirectly calculated. If that's
Any other questions?
I think Claudio have one. Yes, I think the same as what Abhisit have previously presented. So it's not actual address to address. We group the address to form a user. Yes, yes. Yeah. So, right.
Great. Thank you so much, Krongthum. Thanks. Let's thank the speaker again. With this, I end this session on network analysis, and I pass on to Mattia, who will be chairing the next session.
Hi everyone, we're going to start with session number 4 on DeFi, decentralized finance. We have 3 talks in this session. The first talk is by Vimal Teja Mane from the University of Texas. The topic is decentralized payment optimization for scalable microservice transactions. I do not actually know whether the speaker is here. Probably not. I don't know. We didn't consider him for the online talk. No. Okay. Okay. Then we can skip and go to the next one. The next one is Shreyas Chaudhary from TPCT's Terna Engineering College. And the topic is CBDC for Intelligent E-Subsidies, a framework for transparent, dynamic, and purpose-bound welfare distribution.
So hello everyone, my name is Shreyas Chaudhary and I am from TPCT's Terna Engineering College, and my research topic is CBDC for Intelligent E-Subsidies, and this work is jointly authored by myself, Aditya Ghamat, and Dr. Siddhant Hariharan. So basically how this starts, So the traditional subsidy method that is used in India is considered as a leaky pipe. And why is it considered as a leaky pipe? So main problem is that the funds are static. The funds are allocated to citizens in a static manner. And there's leakage between the fund while it travels from the government to the citizen. So in India, the system functions in such a way that the government allocates funds to the citizens, and that fund travels through multiple levels to reach the citizen. And till it reaches the citizen, there's either some kind of leakage, like frauds may occur, or sometimes corruptions may also occur, which may lead to leakage of funds. And even if it successfully reaches the citizen, there's no guarantee that the fund that has been delivered to the citizen is being used in the correct manner. So the main problem is being solved with this unified framework, with the help of with the help of 3 layers architecture that I will discuss later. So first, these are the 3 research works which we have referred to, and the main gaps which we have found is that first research focus only on the energy markets, that is trading of energy. Second, there is only theoretical research on that topic, which we are solving with our paper. And the next is scalability issues, like to scale it on a government level, we are solving that issue. So we are using a CBDC to solve this issue of fund leakage. And the core concept is we are applying smart contracts on a permission distributed ledger technology to design purpose-bound and time-bound e-subsidies that dynamically reward civic behavior. So the architecture is divided into 3 layers, where the first layer is a permissioned DLT, which stands for distributed ledger technology. And this, why we are using a permissioned blockchain, is because it ensures immutability, it has role-based access, and it has compliances that it can be used for government operations. The second layer is the smart contract layer, which will hold mainly the programmable logic. It enforces rules, handles all the static, purpose-bound, and dynamic incentive-based subsidies. And the third layer is the intelligence layer, which is the main layer, which mainly makes the entire system intelligent, and it consists of 2 parts. The main part is the reinforcement learning part, which learns along with past experiences from the citizen and the fund which have been distributed to the citizen. And the second part is graph neural networks, which detects the fraud. If there is any kind of anomalous behavior, then it detects it based on the past occurrences. So the question is why we are using a permissioned blockchain and not a public blockchain. So public blockchains like Ethereum, they lack specific controls that is required for government a government implementation. So that's the reason we are considering permission DLT, mainly the Hyperledger fabric, for this reason. And permission blockchain allows access control that only authorized entities can be validated in the network, and it ensures privacy, that the citizens' privacy is maintained, and compliances that is required for government. The second layer consists of the programmable smart contract. The programmable smart contract is divided into 2 types, and the subsidies are divided into 2 types. It's static subsidies and dynamic subsidies. In static subsidies, there are 2 types, purpose-bound and time-bound. For purpose-bound, it's like a subsidy which has been distributed for a particular purpose should only be used for that particular purpose. For example, if a subsidy has been distributed for electricity, then that token which has been released to the citizen can only be used to pay future electricity bills only. And same with gas and water. So that's purpose-bound. And for time-bound, every token that has been released to the citizen is valid for a particular time and can be used within that time period. If it is not used within that time period, then it expires. So, and the second part is the dynamic subsidies. This is the main part of this entire model. So it responds to real-time events that happen in the real-time situations. For example, we take during a higher grid stress. For example, if a city is experiencing high grid stress, then the smart contract verifies the user electricity usage through the smart meters. And once it verifies and the entire thing is verified, the tokens are distributed to the citizen. And the third layer is the AI-powered intelligence. This consists of two parts: the reinforcement learning part, which is the dynamic engine. It uses a deep Q network which analyzes consumption patterns to optimize incentive values. It learns a particular spot that will maximize the civic participation without overspending. And the second part of this AI-powered layer is the graph neural networks. The graph, it is the guardian of the entire system. It monitors the ecosystem as a multi-relational graph. It detects sophisticated frauds and anomalies that simple systems cannot detect. The DQN is mainly used for incentive optimization. So for example, if government provides high incentives, then it brings a feeling in the minds of citizens that they need to work upon that. So the government tries to maximize the incentives based on the behavior. So for example, in situation of a grid stress in a city, if the load is greater than 90%, like the energy consumption for the entire city is greater than 90%, that could lead to blackouts. So to prevent that, the government will check if the load is the system will check if the load is above 90, and if it's above 90, then the reward amount will increase. And secondly, the deep Q network learns the sweet spot. It's like the point which decides whether the minimum reward necessary is related to the power reduction. So how this problem is solved? If funds are low, for example, if government has low funds, then the AI will automatically adjust to minimum subsidy values to be provided to the government. Sorry, to provide it to the citizen. And it's not static, it's dynamic. So if a user, suppose if a user rejects an offer today for subsidy, then the AI learns to offer more subsidy for the next grid stress event. This is the fraud detection layer, which is the guardian layer. It checks if the system, if any kind of anomaly occurs in the system. So how it does it? So it checks if the consumption deviation is high. If suddenly the electricity consumption drops by 90%, then it flags it as anomaly. Also, it checks the wallet age. For example, if an account is created minutes before the subsidy events are flagged, then it is flagged as a high-risk bot. And one more thing, if the graph neural network basically analyzes relationship, it treats user as nodes and transactions as edges. So this helps it to detect suspicious structures rather than just numbers. So how it does it? It checks the transaction velocity. If funds are moved out of a wallet 1 second after receiving the subsidy, the edge is flagged as money mule activity, and it's considered as an anomaly. And the graph density is also checked. Multiple wallet connecting to a single IP address or physical location indicates a cyber attack. So this is the system architecture. This is the entire thing which I explained. So it consists of 3 layers which I told. The first layer is the hyperledger fabric. The second layer consists of programmable logic layer, which is a smart contract layer. So the second layer gains data from the utility provider. Here utility providers are the service providers like the gas service provider, electricity provider. So it gains data from those providers in form of smart meters. The smart meters send those data to the smart contract, and then the smart contract validation logic is applied on it, and if it meets a certain condition, then the dynamics grid saver bonus is distributed to the citizen. And in the meanwhile, when all this process is going on, the AI intelligence layer also checks each transaction and find any kind of anomalies if present. So the main use case is the grid saver bonus, as I explained. So consider an event of high peak load in a city. So during this event, a grid stress exceeds a defined threshold for the entire city. If it does, then the action is taken. For example, if the smart contract identifies if any user reduces his energy consumption by 12%. So if the user reduces his energy consumption by 12%, then he will be automatically eligible for the reward. After the validation, if all the things are found valid, then the reward will be sent in form of tokens into the CBDC wallet. So what is the outcome of this entire process? So it reduces load on infrastructure while financially rewarding the civic behavior of the citizens. So this is the system flow for the grid stress event. Here the utility provider reports usage data to the smart contract. The smart contract applies validation and verifies if the electricity consumption is reduced by 12%. If it is reduced by 12%, then the token is credited into the citizen's wallet. After the token has been credited, it is either time bound, so the user has to spend it within a particular time, and it's purpose bound. For example, if the token is issued for gas as a gas subsidy, then it can be only spent for gas subsidy and within the specified time. After that, it expires. And here the expiry is checked. If it's not expired, then it is used. And after the payment is successful, the transaction data is sent to the AI layer, which processes the data to check any kind of anomalies. If any kind of anomalies is reported, then the behavior is flagged. So we have run a small synthetic simulation for this particular thing. So we considered 100 households with 5 grid stress events. So we considered 5 grid stress events because the grid stress events are not frequent. It occurs once in a while. So for that reason, we considered 5 grid stress events. And on running this, the output that we got was the average reward we experienced per event was 1316 rupees. And the fairness index was 0.94. So this indicates that the fairness was pretty good as compared to pretty good in sense of distribution of resources among the people. And the cost reduction which we saw was 15.06. The cost reduction here refers to the cost that the government has to spend less for subsidies to the citizen. For validation, we have used Jane's index with 0 being unfair and 1 being the perfect fairness, out of which with our experiment we have got the Jane index for 0.94, which indicates that the dynamic subsidies were allocated perfectly among the citizens. And among the citizens who have reduced their electricity usage, it has been allocated to citizens who have reduced their electricity usage. So the scalability, system validation. So scalability, unlike public blockchains, the permission DLT architecture allows for high throughput. That's the reason we have chose Hyperledger Fabric. And low latency and essential for national scale deployment. Fairness, we achieved a fairness of 0.94 Jane's index. The AI layer ensured that the subsidies are distributed equitably based on actual needs and contribution of the citizens. and interoperability. Modular design allows integration with existing utility providers like the water service provider, gas service provider, and government databases. So the final conclusion, this framework transforms subsidy spendings from passive cost into dynamic investment in civic participation. By combining CBDC smart contracts and AI, we established a collaborative model which model of governance that is transparent, efficient, and fraud resistant. Yeah, that's it.
Are there any questions for the speaker? I actually have one question.
Yeah.
If you watch the first keynote today about the digital rupee,
yeah.
Is it possible, because you're mentioning the permissioned ledgers and so,
yeah.
Do you see your system integrating into something like that?
Yeah. It integrates with digital rupee. The only thing is that the digital rupee that Sir explained in the morning, it has its own logic. We have to define the logic into the digital rupee itself. So if we are able to define the logic in the digital rupee itself, then the system will work perfectly fine.
Because ideally, in the end, you would want to have, let's say, one integrated system that anyone can use. Until this system is achieved, it's normal that people are trying to do their own particular solutions. But long term, you can see that these your effort can merge into something like that. Okay, super. Okay, if there are no other questions, let's thank the speaker. And I call for the final speaker of the session 4, Muhammad Monin Kwazi from the TPCT's Terna Engineering College. The title is Privacy Preserving Decentralized Finance via Zero Knowledge Machine Learning.
Hello everyone, myself Shruti, co-author Moinuddin Kazi, and we are from Terna Engineering College. Nerul. Our topic is privacy preserving decentralized finance via zero knowledge machine learning. In today's world, if you have running a small business and you want some loan to expand it, and you know that your business will repay the loan without showing any credit. But do the banks will give you loan? No, because banks require credit scores. Bank requires credit scores. Also, 97% of DeFi finance, decentralized finance, are over collateralized. That is, you have to lock $2 to $3 for every $1 of loan you take. Why? Because decentralized finance also cannot make credit score decisions without breaching the privacy of the user. So, traditional DeFi lending relies on over-collateralization and disclosure of personal finance, limiting privacy, excluding users without conventional credit records. Our model, that is zero-knowledge machine learning-based framework, use private AI-powered credit scoring with zero-knowledge proofs, verifying borrower risk without exposing any sensitive data, enabling secure, fair, and inclusive lending for all. These are the literature reviews that the papers we have studied. The first one is ZKML, an optimizing system for ML interference in zero-knowledge proof. This actually gives an interface actually demonstrates the feasibility of running ML inferences with zero knowledge proofs using a highly optimized execution pipeline. That is, the ML can be run on zero knowledge, and it can get better accuracy and cost. But it has two limitations. That is, it cannot support larger scale transformer models, and also it has high computational overhead during proof generations. Our model, which uses neural networks, which has three hidden layers, is easier for us. Is actually give better proof generation using neural networks. Second one is scalable zero knowledge with no trusted setup. It introduced task-based proof generations, which actually generates the proofs which actually generates the proof without trusted setup, improving transparency and security. It generates limitations are it generates larger proof sizes than SNARKs, resulting in higher verification and storage cost. So here we use Groth 16 model for our project, which uses limited storage. Always give up to 200 bytes of storage. Third paper is scaling up trustless DNA inference with zero knowledge proof. This shows the deep neural networks can run trustlessly with ZKPs using proof-friendly model structures and optimization. But it has limitations. That is, it does not support for complex activation functions, still expensive for real-time inference. That's why we are using EasyKL. We are converting our neural networks into ONNX, so that EasyKL can be run. Fourth one is SOK, privacy enhancing technologies in finance. This system is using MPCs, FHEs, anonymous credential DTs enable. That is, it verifies the user before user's data before using in decentralized finance. It's actually but it actually limits. It has limitation. The conceptual coverage is broader but not exhaustive, and many proposed PET-based financial architecture still lacks large real-world deployments. So our problem statement is, current DeFi faces challenges in secure, private and fair lending due to reliance on collateral and lack of advanced risk assessment. First is absence of privacy preserved credit scoring, forced to disclose sensitive data to the banks. Second one is over collateralization requirements, insufficient capital and excludes users. Inability of basic ZK checks, cannot handle complex ML-based risk. Result, restricted participation and reduced financial inclusion. So we came up with a solution, that is the ZKML solution. The ZKML-based lending uses zero knowledge proof and machine learning for secure credit verification without revealing sensitive data, enabling confidential, trustless, and inclusive DeFi. Why ZKML is used? Because ZKML has complex pattern. It learns the intricate ML learns the pattern from the features like the transaction history, collateral, and default correlations beyond simple arithmetic. It has adaptive model which adjusts dynamically according to the market changes, and confidentiality model which adjusts dynamically to. It actually it is confidential, that it does not give users data to the on-chain application. The architecture. The first layer is the user layer, where the user has to enter its features, like enter its all details, like its income, how much employment it's required, everything. And this will be, and the user has to give this feature off-chain, that is on its local PC here. Then the ZKML processing will be then done based on the models we will be training, that is neural models. We will be training neural networks after this training, we will be getting some proofs, and these proofs are then checked with the DEFIC protocols and verified there. And if it verified, then we put this proof on the on-chain validations for blockchain verification using smart contracts, and then the process will be done. The technical implementation here, ML model. Firstly, we trained our model on random forest. We used 5,000 synthetic profiles with 15 features to validate feature design and its accuracy. Later on, we realized that random forest cannot be run on EasyKale's framework, so we turned out to neural networks, that is ZKML model. There are 3 layers, 3 hidden layers, 32 neurons, 16 neurons, and 8 neurons with RLUs, plus segment output. It is exported to the Onyx and then compiled by the EasyKale for proof generations. Why Onyx? EasyKale's compiler works directly on Onyx graph. So using Onyx is what makes it possible to turn this 15 features credit model into Groth 16 circuits for proof generations. So this is how we converted our neural networks to R1CS, that is rank 1 constant system. The input was of 15 features. There were 3 layers for neural networks. First one is hidden layer. That is hidden layer 1 of 32 neurons. Second layer is of 16 neurons, and third one 8 neurons. And after this, we will get the output of 1 neuron, which is sigmoid. The first step is neural network expression. This expression H equals to ReLU W dot X plus B, where the W is weight connecting between the input to the neuron, and X is the input feature, and B will be the model parameters. We expand then, after getting the value, we will expand this into arithmetic operations. That is T equals to W into X, where T is intermediate multiplication value and S is linear sum before activation. To convert into R1CS constants, there are 4 operations. That is multiplying weights, then we have to add the bias, then we have to perform RLU gets, and then the RLU binary selector, where the value of R is 0 or 1. If R, the neuron is active, and if not, the neuron is not active. And to verify the neuron, the values should be equal, like W dot, all the values for the arithmetic operations are similar. Now the cryptographic circuits and Groth 16 proof systems. How this circuits works. So I explained that R1CS, the neural network which uses 15 inputs, 3 hidden layers, 1 output, is compiled to rank 1 CS, a system of polynomial equation that turns the model satisfies. So it undergoes all the operation. Now the R1CS will go to the Groth 16 for the proof generations. Here why are we using Groth 16? Because it is seconded. That is the values are true and verifiable. 1.2 KB proof versus 100 plus MB raw data. It is fast on-chain verification and no trusted setup after initial ceremony. Like EasyKale will handle it. The R1 constant will then generate the proofs, and then it will compact the certificate, that is 200 bytes proof. After this, that will be giving the proving statement. It will be giving the proving statement that will be output, which will be given to the smart contracts. That is, I ran the model on secret inputs and got claimed output without exposing any input to the inputs or weight to the smart contracts. Here is the workflow. The user will provide all the input to the ZK snarks, and then it will be submit the private inputs to the ZKML model interface, where it will run it will run on neural networks converted into R1CS and then Groth 16. The proofs will be generated, that is zero knowledge proofs, and then it will be submitted to the on-chain for smart contracts where it will be verified and the lending will be done. The results for this, we actually performed this on synthetic data of 5,000. So result were the testing accuracy was 92.1%, and precision, that is, it actually gives correct data, correct credit score. Recall is also good, that it verifies the input. And also F1 score is 91.3, that is, it does not memorize but also generalize the model. So the model performance was good. And now we are currently working on a real data set for further future. And this is the proof matrices. Like the proof time was 12.4 seconds. The size was 1.2 KB. Sorry, for 2 TPS. Gas cost was 0.8 and verify time was 0.8 seconds. Conclusion: zero knowledge machine learning can deliver high accuracy credit score while keeping both user and model parameters private. Our prototype shows that ZK proofs for 15 features credit model are practical today with sub-second on-chain verification and modest gas cost, privacy preserving, DeFi lending feasible in real deployments. But it has many limitations, like the proof generation latency is high, like 12 seconds per proof, which limits real time for high frequency lending use case. Like the user has to wait for 12 seconds. The on-chain verification cost, that is 2.5K gas per proof, are still expensive and on L1. So we are trying to deploy on L2 to be economical. The current ZKML pipeline supports a relatively small neural networks. Larger or more complex model will increase circuit size and cost. The system assumes that the borrowers supply honest, untampered financial data, protecting data feeds against manipulation. That is, we don't know the user is providing correct data to the machine learning model, that is, it's correct income or not. So we have to verify this with KYCs or any verification layers, because this is not been integrated in our project. But our future scope is like we are trying to deploy it on L2 rollups to reduce verification cost and latency, better for ZK circuits, like improve the ZK circuits with loop tables, custom gates, or new proof systems, so deeper and more accurate models remain affordable on-chain. That real data, which issue we got, we are trying to use DID, that is decentralized ID, to prove the user is verified or not. It's all the features what he is saying is correct or not. And beyond credit scoring, we are generalizing this architecture to other DeFi primitives such as private liquidation, risk awareness, AMMs, verifiable yield optimization, and DIT-based reputation scores. Thank you.
Are there any questions for the speaker? I actually have one question, if I may. The main problem here, as I see it, is actually not technical, but it's more conceptual in terms who holds the real data. So obviously, user has the real data, and whenever data is being submitted to the system, someone has to verify it. Usually, those were the banks or financial institutions. Let's say we can still keep this going. So the idea of this system would be you have one custodian of this financial data which verifies that everything is okay, but everyone else who wants to use it can use the zero knowledge proofs in order to prove without necessarily giving everyone all of the data. Would this be the idea of this?
Actually, we are working like I said that we are using decentralized identity where the KYC and the verification will be done for the users' data. It's all correct and all, and it will be on the local only. This verification will be done locally, not on off-chain only, not on on-chain. So the data will be not shared to on-chain. Whatever the verification will be done, we will be training the ID, decentralized ID, and we will be using on local PCs only. So the data will be not going to the on-chain.
Yeah, super, thanks. Okay, let's thank the speaker. If I may I add just one question. Is this your first conference presentation?
Yes.
Yes. We were all here the first time. I think we all remember our first conference presentation, so I think you did well. So we can give another round of applause. Congratulations. We have some notes from the organizers before we go to the break.
So we have Professor Fujihara, a quick presentation he wants to make about the call for papers for the proceedings of this conference. And after this announcement, we'll break for tea and reconvene as per schedule. We are on schedule now.
Thank you, Vishwas. Allow me to talk before the coffee break. Yeah, thank you. So I would like to shortly announce the call for paper of the proceeding of Blockchain Kaigi 2025. On behalf of editorial board members, I kindly welcome all of you, presenters, including keynote, invited speakers, and general technical talks, and to submit the manuscript to JPS conference proceedings. As you may know, every blockchain Kaigi has published the proceeding in the past 4 years, and submitted manuscript will be reviewed, peer-reviewed, and published with open access format. Also, you don't have to pay any publication fee. Deadline of manuscript submission will be end of March 2026. Please also see the conference web page. I haven't updated yet, but we are going to announce the update about submission website soon. We editorial board members are looking forward to your submission. Thank you for your attention. So let's move on to the coffee break. Thank you.
Yeah, so the tea is available behind the auditorium. Hi, good afternoon. Welcome back to this last session of the day. But this session is preceded by the invited talk from Professor Hidenori Nakazato from Waseda University. He is a PhD in computer science from UIUC, University of Illinois at Urbana-Champaign. And he's a professor at Department of Computer Science at Waseda University. He has experience in industry for more than 15 years and joined Waseda University in 2000. His research interest includes converging networking and computing network protocols and algorithms and their performance issues. So please welcome Professor Hidenori.
Okay, good. Okay. Good afternoon, and it's my great honor to be here, invited as a speaker. Thank you very much. My field is not in particular blockchain, but I have a project which is about digital twin ecosystem, and in that system we somehow utilize a blockchain. So yeah, I was requested to present my experience in this system. So I have like 45 minutes. I don't know, but I can adjust to that. All right. So this is outline for talk today. And first, motivation. Well, I'm not sure whether it is needed, but everybody know that smart city is one of the topic in say in the government, local government, and of course the smart city try to control the life in the city by information technology. So that means that we need to model the real world into the cyber world. So the model formed in the cyberspace is a digital twin. So the real, city in the real space here is reflected to digital twin, and then the city service is created out of or using this model. And what we want to try to solve is that to the continuous and very useful city services, we need updated service, updated view of the city, and that is exploited by information technology. So in a sense, cities now aim to become a city as a service. City try to provide services to citizens. And as I said, that require the digital twin, the model of the city, need to reflect the current state of the world. Current state of the city, up-to-date model. And city is not a small world. It is a big field. So the large, vast field need to be covered, and in addition, we need to update the model all the time. So the question is how we can sustain this updated digital twin, and that covers the vast area. That is the topic. And actually, there are existing projects try to model digital city. These are the model of 3D of the city. All over Japan, the Plateau is a project to make a 3D map of cities, and that is operated by a ministry in Japan. And local government also make effort to make digital twin of the city. And also in the world, Singapore has a model. And okay, so we need to cover vast area and digital twin up to date. That asks for cooperation of many organizations, including local government, maybe companies, other organizations, and even citizens, ordinary people. Many participations required to maintain the digital city, digital twin. And to make this model, digital twin, up to date, we need to create, in a sense, win-win environment among the stakeholders, users, participants, and so we need an ecosystem. So cooperation of many entities, companies, local government, they participate, and they are supposed to own the data. So here we decided to include Web3 technology into the system. As you know that up to Web 2.0, it's like the information is held by the central servers. But Web3, he tried to free from such a superpower to manage the data. Instead, Web3 tried to leave data at the owner's hand. And so we want to make participants reserve the ownership of content, and we won't make it verifiable. Recently, this concept appears, so-called DPIN. And in this concept, participants, contributors share their resources and form and sustain some infrastructure. And this DPIN model at this point usually provided by company, and participants just join the company and try to get some reward. And we say extend this concept of DPIN to form an ecosystem. There are many examples of DPIN. I just listed 2 examples, but you see a lot of icons here. All of them somehow are categorized as DPIN. And Helium is a mobile network creating DPIN. So participants provide the access point, and mobile network expand as participants put base station with their, with their as their contribution. And Hive Mapper is like a Google map, but that is created by, say, ordinary driver. Now cars are equipped with cameras, right? And so they can take the picture of the street and just contribute the video to this project, and they can create a map. So this kind of mechanism is called DPIN. So citizens contribute to as an infrastructure. So this is our project called D2 Ecosys, and this is the title of our web page. And actually, this project was already over, is over now. Ended in March this year. And this project was actually performed by 5 organizations, including my school, Waseda, and 2 more universities in Japan, 3 more universities in Japan, and GaiaX is a company. The goal of this project was this one: constructing the ecosystem to co-create digital twin. And people and organization things autonomously participate in this system. So we want to include some self-growing mechanism in this project. And we want to leave the ownership of the data to the creator. So maybe it goes well with like Web3 concept and probably with blockchain as well. So we want to create up-to-date digital twin is a goal of this project. There are many technical issues. I'm going to cover this later. But here, in this diagram, participate, say they purchase IoT device and say sense and scan the city, contribute data, and then this data is used by some users, and that will be that will make the source of the incentive, and we try to make this a cycle. So this is just a repeat I just explained in the previous slide. At the bottom, this is a city, real city. Citizen scan the city, create a digital twin, and these are the users of digital twins, and they create different services out of the digital twin, say energy management, crime prevention, maybe autonomous driving, and this will create some income to those users, right? And they will provide some source of reward, incentive. The incentive is distributed among the contributors. So this is ecosystem. The exact current implementation, what we do is creating this like this 3D map, or actually this is still point clouds though. This kind of point cloud is created after the implementation of our system. And we are, say, searching the possible application. And initially, what we have in mind is like supporting micro-mobility. And one contributing side, we may be able to create a game to scan the entire city. Say, we have this kind of game already, right? if you know the interesting game titles. There are a lot of technical fields we need to solve. I mean, programs. But in this presentation, I just include the red-colored research field: platform, incentive, and networking. We need to work on the trust and data processing. These are important issues because the cloud-sourced data may not be reliable. So we need some way to make it trustable and valuable. But we didn't have a chance, or we had no time to spend in a project on this topic. And we are working on 3D point cloud. And 3D point cloud includes a lot of data. And we need to align those data. But at this point, we have not automatized that mapping yet. And other issues to be attacked. But in this talk, I just talk about these three issues. Platform. City include vast area. So at the beginning, we may have only a limited field covered. So in the sense that this system needs to have expanding, self-growing capability. This is the underlying mechanism. We have, blockchain here of this conference. And in addition, we have IPFS, interplanetary file system. Maybe you know that this is a distributed file system, and make the data at the owner or the contributor's site. So we chose these two mechanisms as an underlying mechanism. And we use a smartphone, say iPhone Pro or iPad Pro, already equipped with LiDAR. So that LiDAR sensor can be used to scan the city. And using smartphone, we scan the city and upload. And then if we don't have a particular region uncovered, I mean, is not covered yet, then user just scan the place, ask the system using geohash. If it finds there's no server responsible in that field, then say we choose some computer to house a node of IPFS and blockchain, start up those servers, and create additional region. This is a current system. This is a flow when digital twin is contributed. This is a data provider, say citizen holding iPhone. Scan the site, upload to IPFS, and then say what is updated. Say some of the field is already maybe already scanned, but additional scan can improve the quality. So say we make a comparison with the available already scanned data and extract updated area, because the reward is based on the contribution of the contributor. So based on this update, we calculate the contribution. And say using like games theory, theory, and distribute the reward using, say, referencing, both referencing and using blockchain mechanism. This is a contributor side. And this is a user side, data consumer, say the service creator of the smart city. Look at the data catalog, and then say purchase the data. That purchase, that event is recorded at blockchain using smart contract. And based on that event, that this purchased reward source is distributed to the contributor. In the meantime, the data side is here, and the data consumer requests the data and get the data, something like that. As a platform, we use IPFS, interplanetary file system. You know, as I said that we want to leave the data at the contributor's end, so we chose IPFS. IPFS is a peer-to-peer file system, and files are placed into distributed fashion in device. Can be, you know, unused storage space is used, but mostly the scanned data itself is, if it is not uploaded to other servers, the data itself remain in the device. And the content is accessed by the hash value. Authenticity of the content is verifiable using this mechanism, so-called Merkle DAG. And version can be also controlled, managed. And you maybe already know that IPFS is already used at many places, and even there's a browser use IPFS. So it is widespread in Web3 world. That is IPFS. And it's a content-oriented file system. Means that to look for or get the content, you need to specify so-called content ID. Instead of specifying an IP address of a server, just content ID is used to get the data. So that is another point I want you to remember, because we somehow exploit this this feature, and also because of this, it's the tampering can be detected. So that is the kind of explanation about the platform. And incentive mechanism. As I have already said that the point cloud if the same location, same scene is scanned multiple times, it can improve the quality of the point cloud. So say one field is scanned by one person like this, another person scan like this, then we can overlay the 2-point cloud, and that will improve the quality. So many people may scan the same scene, and depending on the part of the point cloud, the quality may be different. And that point cloud is used by the city service provider, and depending on the quality, the cost may be different. And that will be, the amount is paid, and that it will be reflected to the reward to the contributors. Yeah, and we try to make a fair remuneration. This is an explanation that the quality improvement by scanning the same place many times. And depending on the quality, the service provider, which is a user of the digital twin, pay different amount. So we charge differently depending on the quality. And that is sourced for reward to the contributor. And the distribution of the incentive also depends on how much contribution each contributor did. So this mechanism was one of the research topics we have resolved. And another one is networking. IPFS is a distributed file system, and it's name-based in a sense, content ID-based file system. So to find the content, it uses one of the DHT, distributed hash table mechanism, called Kademlia. And Kademlia is used like 2 to 3 times to find the data. And the Kademlia is a DHT. It is pretty slow in a sense. To find the content, many messages need to be exchanged. So here, because my field is my area of interest is networking, so this is a topic I work on. Maybe you don't know what is information-centric networking. Internet protocol use IP address to transmit data. Information-centric networking use the content name to find the content. Right now, the usage of the internet is more often just getting content instead of sending message. So, so for that purpose, information-centric networking is a good match. And what we propose is to replace the Kademlia in IPFS with this information-centric networking. Because in a sense, content ID, which is used to register and look up the data in IPFS, is so-called content ID. And that is a kind of name, if you say consider. It's not the host address, but the content name in a sense. So instead of doing DHT, we replace the IP network with information-centric network. Then say IPFS want to find a certain content. It just put the content ID in the packet. Information-centric networking just get that information. So we replace the DHT lookup by network routing. So we can speed up. That is at the ordinary, expected result. But that's what we did. These are like an overview in a technical part. Say the platform, we use blockchain and IPFS. We have incentive mechanism. We try to speed up networking for IPFS. These are kind of overview in technical sense. But we have the real implementation of this system. We created real smartphone application. Say using iPhone and iPhone Pro and iPad Pro, we can scan and the surrounding of the contributor. And by say superimposing, aligning those point clouds and create digital twin. And we have a site to trade data. Some are written in Japanese. We created Japanese iPhone application. We use iPhone LiDAR sensor. This is a scan of this scene. And these buttons say that the result is acceptable or we need to rescan. And the scan data is uploaded. And iPhone has can detect the location, right? So location information is also uploaded to the site. Say if we don't have the regional server based on the geographic location, it will ask whether to create a regional server somewhere. And this is an upload web page. Well, we have this web interface as well as iPhone interface. And we have some additional window panel which is used for merging the point cloud uploaded. And then, this is a site to trade the uploaded digital twin. And payment is made in cryptocurrency, which is related to this conference. This is just an example. And this is not really, at this point, the merging of point cloud is not automatical because that requires some research. But this site can sell the scanned point cloud, and it has some price and download button. And we utilize, of course, the blockchain smart contract and say to record who contributed, who use the digital twin, and also the event of the payment by the user, and also the distribution of the reward. Yeah, and this is, in a sense, once event happens, the recording of the event is need to be automatic. In a sense, it is made into a transaction. So we utilize a smart contract to make this automatic. And related to this mechanism, I cannot say that I created, but yeah, we made ITU standard just in this September. Nowadays, I guess India is trying to make international standard. We have a lot of Indian people participating in the standard meeting, so maybe you can contribute some. Yeah. And we continue to do this like already 3 years. And this is what we learned from our project. Well, I'm not the position to say this, but you already know that blockchain system have matured. It's usable in the real world. But when we apply blockchain to our system, as you see that we created servers because we cannot handle, if we assign each individual user as a peer, it will be overwhelming the system. So at this point, we say make servers to participate in blockchain, and also IPFS node as well. Yeah, and we say use technology, but in particular, we need to make this system usable by ordinary people. We need to make it one-touch or zero-touch system. And for that purpose, we use container technology a lot. We are having some program in peer-to-peer distributed storage network, that is IPFS at this moment. Yeah, where to save the data is a problem, because point cloud generates a huge amount of data. So it consumes a lot of storage, and that need to be controlled. And in particular, peer-to-peer file system, nodes are not reliable. Nodes may drop out, and the data may disappear. How we overcome is a question. And since this is still a prototype, we need to validate whether this incentive mechanism really works, incentive design is really works. And as I already said that the merging point cloud requires some still to automatize that the mechanism is a problem. And the biggest problem, biggest issue we have is that, say, killer application, good use case of that system. And after that project, we have another project, which is a continuation of the previous project, and we are now we are running this project. The consortium is a bit different. Waseda and Institute of Science Tokyo, GAIAX included, and K3 Deep Innovation provide a service using IPFS and make it more secure, the kind of company involved. And yeah, in particular, this is a focus, new storage network, high elasticity and high security. And this project is also from one of the Japanese National Research Institute, and they has so-called secure off-chain storage. And we are asked to use their mechanism in our system. So we are trying to incorporate that mechanism into our system. So our focus is here. On-chain, blockchain is not an issue at this point. We are focusing in this off-chain part. We used to use IPFS, but we need to incorporate NICT, secure off-chain storage, and also we are trying to incorporate information-centric networking as well. Okay, I guess I spent 38 minutes, so it's time to conclude. Digital twin co-creation system, I introduced the system. Our system has a mechanism to maintain the city digital twin up to date with the cooperation of citizens and other organizations, include incentive mechanism, and yeah, we are trying to make ecosystem. In a sense, our system extends the deep in concept and make it totally decentralized. Finally, we need a showcase or killer application to make this system really runnable or sustain in the real world. Okay, thank you very much. Any question?
Thank you very much for giving us a curious presentation. I have a quick question about cyber security issue. So, if a terrorist becomes a member of this project and the terrorist access to the 3D point cloud data and use a drone to attack residence of the important person. So that kind of thing can be happen. That is a really killer application.
Okay.
So could you tell us the possible countermeasure for the cyber issue?
Okay. Since the digital twin, this system is an ordinary, say in a sense, database. For security, the countermeasure is like a usual information system countermeasure need to be applied to this one. Over that, right now in the current project, IPFS is somehow changed, and in this new file system, data is even cut into smaller pieces, encrypted and distributed. So if you don't have the authority to access the data, it will be harder to get access. At least that is the current, countermeasure. But security is more, the biggest security issue is the human, right? Once the authorities stealed then it will be hard to prevent. Yes.
Thank you very much.
My question would be like, because of you said this one is more like wanted to have up-to-date scan of them, but I cannot see this up-to-date incentive in your workflows. I mean, for example, if someone scan a particular area and then they receive some money, how can they know like this one need to be updated in the future, for example?
You're right. So when at the trading side, we just show that when that is scanned, you know. So at this moment, that is what we do. But yeah, you're right. Because although we have a mechanism to update the digital twin, but it's up to the contributor. So that is difficult to control. So if we can get, if we can provide better incentive, then if the contributor can earn more, probably. But yeah, that's the answer. Sorry for that.
Professor Nakasato, I had a question. Thank you very much for the presentation. Very interesting project, also linking physical assets with this digital environment. My question is, there is a layer of incentives, but it is devoted mainly to the blockchain part, or is mediated through the blockchain implementation. And my question relates to why the use of IPFS, because IPFS provides no incentive for storing this asset, this data or this information into the hard drives. Why this was the suggestion and not something like either Filecoin or ICP, whatever it is?
One of the reasons we adopted IPFS is that IPFS originally leaves the data at the creator's site. So we want to make the ownership the creator. That is why we adopted IPFS. And as you said that, one issue we are working on is that in this incentive cycle, we include the contributor of the servers as well. Then we somehow improve the availability of data because the provider of the server also has an incentive to make the server available. And in that way, we probably can keep the data without losing it.
Yep.
Yeah,
Okay.
so that's a part of our project.
Fantastic, thank you very much.
I have one question. As you mentioned the term city as a service.
Can you speak up?
City as a service,
Yes.
you mentioned one term, okay. So suppose if I consider one service like the wastewater management in the city, the urban area. So in that case, what is the, and also you mentioned that there are different standards, that should be applicable worldwide if we go for the applicability of the digital twin for the particular service, okay. So my question is, if I go for these wastewater management issues and suppose we have collected some geospatial images, so what are the other difficulties we can face to solve this kind of problem and how digital twin can ease these issues?
Waste management.
Basically, I'm focusing on the sustainability, and one part of this is the wastewater management.
See. I'm not too sure how to answer. Well,
initially, when I started working on that particular problem, means we had the water resources in our mind to collect as the information. So, as it is the wastewater, so we had to consider all the water sources available in the urban area, in particular range of the areas we consider. So, in that case, means how if I go for the simulation in the digital twin platform, and what are the data we actually need, how to collect, and how this digital twin will come into the scenario for this. Because
Okay.
it has application on that solving this, but that was not, I was not able to link that.
So you talk about water. Because we are just, you know, what we have in mind is like 3D maps. So, you know, how we can connect to the, say, waste management or the water. They require different kind of sensing probably. And but at least we have a mechanism to include such a sensed data, but how we incorporate that kind of sensed data into our incentive mechanism probably need additional consideration. Yeah.
Okay, I'll go to one-to-one discussion with it on detail. Thanks.
Thank you. Let's thank the speaker.
Thank you very much.
And I invite Professor Fujihara to felicitate our speaker.
Oh, thank you very much.
Please
Thank
come
you
on
very
this
much.
side.
Yeah, please.
Laptop काढल्यामुळे. Thank you. So I invite Professor Chakrabarti. So he's the next session chair.
So welcome to today's final session, and we have 3 presentations. 2 of them are online. So first presentation of this session is by Professor Roff. He is from University of Zurich. So he will be talking on the global development of a stablecoin regulation. So the floor is yours.
Thank you very much for the invitation to the IIT Bombay. I appreciate very much that I can give a short presentation here. But I have to warn you, after 8 hours of technology, you are now confronted with law and regulations. The only comfort, you will only have to suffer for the next 20 minutes. Now, my topic is global regulatory developments of stable coins. Very obviously, I can not go into all details which could be addressed in this context. I would rather like to try to give you an overview of the regulatory principles and let you know what else you could read if ever you are interested to dig more into these topics. Stablecoins are payment tokens pegged to and collateralized by a reference asset, in most cases a fiat currency. Typical reserve assets used for collateralizations are highly liquid financial instruments denominated, as I said, in fiat currencies. Therefore, stablecoins are in fact in a position to at least partially compete with traditional payment systems, and that's also the reason why many central banks are relatively hesitant to see the stablecoin developments. I will come back to these aspects. Stablecoins can be used to store value as other assets or as direct payment means. Stablecoins with a value linked to existing sovereign currencies may serve as an alternative to the well-known cryptocurrencies such as Bitcoin, Ether, Ripple, etc. The name stablecoin gives the impression that these coins are stable, but in practice has shown that this is not always the case. In particular, the algorithmic stable coins have turned out to be very instable, as we have seen in the Terra and Luna case. Business models have mainly developed in the United States. The most well-known are UCDC, run by Circle, or UCDT, run by Tether. And how do they make money? On the one hand, they can gain profits from staking certain stable coins, or they ask for a certain fee for the depositing of stable coins, or they ask for a fee, as is the case with the stablecoin UCDT. Somehow, apparently, my picture has disappeared. And now it has gone too fast. I would like to start with some regulatory approaches, and our first remark concerns the fact that, as you of course know as technology experts, we are confronted with the trend from centralized finance to decentralized finance, CFI to DeFi, and this has a very important consequence on regulators and supervisors, because as long as we have centralized financial systems, the intermediary being responsible for running the system or for offering services can be regulated and supervised. This is not anymore the case in DeFi business models, because in principle, as the name DeFi says, we don't have an intermediary, so we don't have a subject who could become the addressee of supervision and regulation. In principle, the regulator would have to impose certain compliance and behavior measures on the providers of the services. But since the providers as such are not easily identifiable, in principle, as a consequence, services would have to be regulated. And this is, of course, very difficult. And so far, I do not know any country which was successful to change the regulatory approach, which would in principle be necessary if more and more services are offered in a DeFi model. And this is particularly a problem if we look at traditional regulatory objectives, such as investor and consumer protection. What do we have at stake in this context? For example, protection of the investment. Usually, if somebody invests in a bank, this investment is covered, at least to a certain extent, by a deposit insurance, or by the fact that, for example, shares and bonds can be surrendered from the bankruptcy estate. If we are living in a DeFi business models, these caveats for investor protection do not anymore function. In addition, in a world of 24/7 hours offerings of financial services, information asymmetries cannot be overlooked. Providers should give the information to the investors. However, the providers are hard to identify. I think I didn't touch this one. I don't know why it disappears all the time. And this is another regulatory issue which cannot be easily overcome. And this has led to the situation that we have been confronted with many uncoordinated regulatory activities in the past. Regulators in different countries started to introduce rules at this and that occasion. However, there was no overall concept which has helped to really come to coordinated regulations. And let me just take an example from Switzerland, my home country. The very first stablecoin project was launched in Switzerland, and this was due to the fact that Facebook decided to start its Libra stablecoin project in Geneva, Switzerland, and at that time, 2019, the Swiss regulator was of the opinion that stablecoin would be a payment infrastructure, which in my opinion does certainly not meet the purpose of stablecoin projects, and the problem has been solved insofar as Facebook decided first of all to narrow down the Libra project, and secondly, after it has been renamed to Diem, has completely withdrawn the project, and therefore the intended regulations which have been prepared by the Swiss regulator never came into place. A special topic in this whole context is anti-money laundering provisions, that a extremely difficult topic, and that's in fact also an issue where law relations on the one hand and technology meets. I will come back to that at a later stage. The global regulator here is the Financial Action Task Force, the FATF. The FATF has included virtual assets in its recommendations already 5 years ago, without explaining how the control process should really be implemented. The FATF also introduced a so-called travel rule, which means that the holder of assets in a custodian wallet has not only to check who would be the originator of the respective virtual asset, but also the beneficiary of these virtual assets. And this leads me now to the first overall regulation, which is MiCAR, Market in Crypto Assets Regulation, from the European Union. MiCAR was published in 2024, so it's a little bit more than a year old. A couple of provisions have been put in force more or less immediately. Other provisions will only come into place after a certain time. And MiCAR, in fact, was seen as a regulation which should have an impact on various countries around the globe. Usually we call this cross-border impact as a Brussels effect. Brussels effect has been coined as a term after the European Union has implemented the General Data Protection Regulation, the GDPR, in 2016. Since many countries, and not at least East Asian countries and the ASEAN organization, have taken over various provisions from the GDPR and have also recommended the East Asian countries to implement similar provisions in order to reach a harmonized level of data protection. The same is true for the Cyber Resilience Act, and the EU is hoping that this would also happen with MiCAR, because MiCAR is arguably the world's most comprehensive regulatory framework and is already changing parts of the cyber environment. MiCAR distinguishes between 3 different types of tokens, the so-called ART, the asset reference tokens, here mainly instruments which are close to traditional financial instruments. Then the EMT, the e-money tokens, in particular stable coins, and the third category concerns the other cryptocurrencies. So we are in the context of the e-money tokens, the stable coins, and for the issuance of stable coins, a license is required under MiCAR. Supervision of the providers of stable coins is foreseen. The providers of stable coins are called crypto asset service providers, CASPs, in abbreviated form, and the CASPs do have to comply with a large number of obligations. MiCAR tries to realize the regulatory framework in a way that it is technology neutral, and that the principle, same business, same risk, same rules applies, which in fact make sense. The next two slides lists many countries which in theory could now be presented here, but as I said at the beginning, I do not really have the time to go into the details. But for those who are really interested to dig in the details, I may say that I wrote an article which will be published in the Banking and Finance Law Review in about a month, and whoever is interested in this article can give me the mail address, and I would then send the article. This allows me to be here very short before I get the red card for taking too much time. I think the United States are really an interesting example, however, to quickly explain. The Biden administration was very reluctant to accept stable coins. Biden released a respective executive order. With the Trump administration, the picture completely changed. Trump has nullified the Biden executive order, has issued himself an order which should promote the development and growth of lawful and legitimate dollar-backed stable coins in the United States. Trump has appointed a working group on digital asset markets, and two main legal instruments are either implemented or on the way to be implemented. The first one is called Guiding and Establishing National Innovation for U.S. Stablecoins Act. That's the so-called Genius Act, which was adopted by the Parliament. And this Genius Act defines the permitted stablecoin issuers. And then on the way is a second legal instrument, the Digital Markets Clarity Act. And finally, a further instrument which should be implemented is the Anti-CBDC Surveillance State Act, and this clearly shows the policy change in the United States. The Trump administration is very much in favor of stable coins and is completely against state CBDCs, and that's a very different approach from the perspective taken, for example, in Europe, regulating stable coins to a far extent, and also, for example, in China, pushing very much state CBDC. Then Canada, United Kingdom do have certain rules, which I do not go to explain. Switzerland, already mentioned, had the Libra project, and new regulations have now been proposed on October 22nd of this year. Possibly I can mention a few words tomorrow during the panel discussion. India, I don't have to bring oaths to Athens. You have heard this morning that India is preparing to launch an asset reserve certificate, a rupee-based, fully regulated private stablecoins, which should run in parallel with the intended digital rupee, the CBDC. The launch is planned for the first quarter of 26. Hong Kong, which is quite an interesting approach, issued a stablecoin ordinance in May 2025 for fiat reference stablecoins issuer in Hong Kong. And Singapore and United Arab Emirates also do have certain regulations, in particular the Payment Services Act. In Singapore, stablecoins can be issued in relation to Singapore dollars and the fiat currencies of 10 nations, namely the G10 nations. United Arab Emirates foresee in the Payment Services Act that the stablecoins must contain a reference to the United Arab dirham, so the national fiat currency. What about the future of stablecoin regulations? In my opinion, it is really important to develop a stringent regulatory classification, because not each stablecoin merits the same rules. If we, for example, do have stablecoins which are collateralized and stablecoins which are not collateralized, then we need different legal rules. If we have algorithmic stablecoins, the public must be informed that algorithmic stablecoins are not at all stable. And if you have tokenized funds, then we are relatively close to our traditional securities regulation. If a one-to-one linked stablecoin linked to a fiat currency is issued, the investor must be protected that he will get the money back as a basic requirement for regulation, which, by the way, as I mentioned before in the context of MiCAR, should be technology neutral and should comply with the principle same business, same risk, same rule. As far as the regulatory needs are concerned, as I mentioned just before, it is really decisive for the survival of the regulatory framework for stablecoins, that the right to repayment is foreseen. So the amount paid for a stablecoin should be secured by segregated funds or by a resilient corresponding default guarantee. Staking income on stablecoins should be regulated, and segregation of customer assets is a key aspect. Finally, and as I mentioned at the very beginning, we need technically appropriate AML provisions which are based on new technologies. Just a remark, since we do have Japanese colleagues here. Following the collapse of Mt. Gox and the hacker attack on CoinCheck, the Japanese Financial Services Agency implemented the separation of customer assets combined with fiduciary management of customer funds and safekeeping of customer tokens. And this has led to the situation that Japanese investors did not so much suffer from the FTX collapse. So Japan has given an example how regulation could be designed. I see that my time has run out. I do not extend any further, and I refrain from giving you an outlook in this context. Thank you very much for your attention.
Thank you. Time for questions.
thank you very much for the comprehensive presentation. One question that I have is, United States is actually using the way in which it is regulating the stable coins in a way that also debt bonds are also acquired by the issuers of the stable coin. Is it a practice that is happening elsewhere as well? And what is the impact that you think that this kind of approach will have in the market, but also in the incentives that different countries have to release their own stable coins?
Thank you for the question. Very difficult. First of all, the US dollar is, of course, the most important currency which we do have in a traditional sense, and this also facilitates the issuance of stable coins having pegging to the US dollars. However, apart from this economic fact, the Trump administration is introducing a relatively lenient regulatory framework, and this is, of course, to the advantage of the providers of stablecoins, less burdensome, not so many obligation. But the backside of the medal is always, if something goes wrong, a damage could occur, and in particular, the United States do not have, at least until yet, introduced rules which would give full investor consumer protection in case of a collapse of the provider of stable coins. In principle, according to MiCAR, but also according to the Hong Kong ordinance and to the Japanese legislation, the investor should be fully protected, because either the funds are deposited and available, or a bank is issuing a guarantee. And this is not the case for the stable coin project in the United States. Insofar, lower regulatory burden, but relatively higher risk for investors.
Okay, let us thank the speaker. Let us move to the next talk. The next speaker is Pratik Khanna. Pratik is from MIT University. So he will be talking on blockchain-based registration of message as legally admissible proof of communication.
This. Oh, you need HDMI. HDMI is not there. I have it in pen drive if you want. No, it won't go. It won't go. I'll copy it in the pen drive. Try putting it there. Try putting. I put it on this pen drive. Good evening, everyone. My name is Pratik Khanna. And the presentation is titled Blockchain-Based Registration of Messages as Legally Admissible Proof of Communication. So the problem that we are trying to solve is digital messages being relatively easy to alter or fabricate. Courts require proof of authenticity, integrity, and a clear chain of custody. Existing systems rely on centralized servers which can be manipulated. Okay. So there is a need for a tamper-proof, time-stamped, independently verifiable system. Indian Evidence Act and IT Act require reliable digital evidence. Rising instances of cyber disputes, commercial disagreements, and contract breaches raise the relevance of the system. There's a lack of standardized digital notarization infrastructure. Blockchain offers immutable records and verifiable timestamps, which can facilitate resolution of this problem. The objectives are designing a blockchain-based message registration model. It ensures immutability, non-repudiation, and forensic traceability. We integrate hashing, digital signatures, and metadata preservation. It carries evidentiary reliability vis-a-vis the traditional systems. So the existing challenges are deletion or alteration of communication, manipulable metadata, for example, email headers, timestamps, dependence on third-party servers, difficulty proving chain of custody, and high cost of expert forensic verification. Why blockchain? It offers immutability. Records cannot be altered retroactively. Decentralization. It removes single point of control. Consensus-based validation provides for trustless verification. Timestamped entries, which are cryptographically ensured. And non-repudiation, as digital signatures tie messages to the sender. The proposed architecture consists of on-chain and off-chain components. On-chain contains message hash, sender's digital signature, timestamp, and metadata such as sender ID, message type, and channel. Off-chain components contains original message content and attachments such as multimedia and supporting documents. The workflow is as follows. User drafts a message. The message is digitally signed. Hash of the message plus metadata is generated. Hash is written to the blockchain ledger. Message content is stored off-chain. And validation can be performed by rehashing the original message and comparing it to the blockchain content. This is the architecture. The user sends in a message which can take various formats. The message is stored in the off-chain storage. Then the processing component computes the metadata and also the hash and stores it into the blockchain component, which is the on-chain component. The verification process proceeds by rehashing and comparison, thereby providing a proof of authenticity and integrity. In terms of legal alignment, Indian Evidence Act Section 65A and 65B require proof of authenticity. IIT Act 2000 recognizes digital signatures and e-records. Bharatiya Sakshya Adhiniyam Sections 62 and 63 provide for legal admissibility of electronic records. Blockchain ensures identity verification, data integrity, and reliable timestamps. Comparing it with traditional systems, in terms of integrity, the traditional systems can be easily tampered, whereas blockchain-based systems are immutable. Timestamping is manual in traditional systems, whereas it's cryptographic in blockchain-based systems. Authentication requires experts, whereas blockchain-based system has built-in identity verification. Chain of custody is weak in traditional systems, whereas it's fully auditable in the blockchain system. Verification cost can be very high, as it involves involvement of formal forensic experts. In blockchain, the verification can be carried out very easily. The scalability of traditional systems is limited, whereas in using contemporary technology, blockchain-based systems are highly scalable. Blockchain security features cryptographic hashing, public-private key digital signatures, distributed consensus, audit logs, and chain of custody, and resistance to tampering and deletion. Let's take a look at a use case. Party A sends a contractual instruction to Party B. Later, the instruction is disputed. The way we can use the blockchain-based system for verification is we retrieve the original message, recompute the hash, match with the blockchain entry, confirm timestamp and digital signature. If they match, then the claim of Party A is valid. The implementation can be carried out on public blockchain platforms, enterprise blockchains, government-managed blockchains, and it can be integrated with third-party services such as email, WhatsApp, SMS, and enterprise chat. Some of the limitations of the current system: it cannot prevent false content before signing. It requires user authentication to avoid misuse. There are on-chain data privacy concerns and blockchain scalability and cost concerns. To conclude, blockchain provides a reliable, transparent proof of communication system. It strengthens evidentiary value under Indian legal standards. It enhances trust, reduces disputes, and speeds up judicial processes. It represents a major advancement in digital evidence management. In terms of future research, the system can be further enhanced by using zero-knowledge proof systems for privacy, smart contracts for automated legal compliance, cross-jurisdictional digital evidence frameworks, AI-assisted message authentication, and integration with digital identity initiatives such as Aadhaar-based signing. Thank you.
Okay, thank you. So time for questions. So if there are no questions, let us thank the speaker again. Our next two talks are online. So next speaker is Takayuki Watanabe from Tokyo Women's Christian University. The talk is on toward a Web 2, Web 3 hybrid infrastructure for trust visualization in social media.
हेलो लैपटॉप को ऑडियो ऑन करना लैपटॉप को ऑडियो ऑन
वीडियो बंद करो ना स्पीकर म्यूट
You can see my slide? Can you hear
yes,
me?
we can see you. Yeah, we can see your screen also. We can start.
Okay, so I'll start my presentation. Good evening. Social media has its good and bad points. With the advent of social media, the era of Web 2, where you can read and write, has begun, and everyone has been connected through social networks. However, social issues such as fake news have recently emerged. The problem is how to determine the trust of social media information. I think what is lacking in today's world is a socio-technical infrastructure that cryptographically verifies trustworthiness while minimizing exposure to privacy risks. My proposal here is, can we solve the issues of Web2 era social media by applying Web3 technologies and philosophies? Digital identity is key there. Trust of social media is indicated by trust of poster, and trust of its digital identity is the key in trust of poster. Quintly also says, digital identities are the key to how we can solve the fundamental trust issues with today's internet, in his book, Learning Digital Identity. The first prototype I created at ISA Tokyo Hackathon is ZKVC. The source code is available on GitHub. ZKVC links a digital identity called DID to a social media account. It also links the verifiable credential VC to DID. EIP 1056 is a smart contract to handle DID and VC. It protects privacy through the selective disclosure of credentials using ZKP. That information is cryptographically verifiable. The display of trust is still under development. Keywords shown in bold on this slide will be explained in the following slides. The first keyword is DID, which stands for Decentralized Identifier. DIDs are a kind of cryptographic identifier that solves the problems, and they provide one of the fundamental technologies of self-sovereign identity. DID specification is defined in the W3C. DID characteristics are non-reassignable, solvable, can search for more information about DIDs, cryptographically verifiable, and decentralized. The next keyword is VC, verifiable credentials. A credential is a structured document containing claims. Claims are name value pairs representing an attribute of some sort. The VC specification is also defined in the W3C. People rely on one other important thing. We call that reputation. The other way we rely on what others say is using credentials. That's why credentials are important. There are three roles of credential exchange: credential issuer, holder, and verifier. EIP 1056 is the Ethereum lightweight identity smart contract proposal. Its example code is implemented as 3 parts on GitHub. They are EtherDID display, EtherDID resolver, and EtherDID. The functions used by GKVC are register DID, get current DID, resolve DID, issue VC, and verify VC. ZKP stands for zero knowledge proof. In cryptography, a zero knowledge proof is a protocol in which one party, the prover, can convince another party, the verifier, that some given statement is true, without conveying to the verifier any information beyond the mere fact of that statement's truth. The H verification process was carried out in the following steps. First, I designed an arithmetic circuit using the Circom language, where the birthday is the private input, today's date is the public input, and the constraint of the H is 20 years or older. Next, GK snag, zero knowledge succinct non-interactive argument of knowledge, and PRONC are used to generate proofs by performing multi-step calculations. H verification can be proven either on-chain or off-chain by reading the birthday written on the vc.json. This figure shows a rough architecture of ZKVC. DID is linked to the social media account. The DID document is recorded in the DID registry on the Ethereum blockchain. And the EIP 1056 contract writes, reads, and verifies the DID document. The VC linked to the DID is stored locally. EIP 1056 contract reads the VC to verify its authenticity. The ZKP circuit privately reads the birthday recorded in the VC and verifies the H with ZKP. The ZKP application consists of API server that communicate with EIP 1056 contract and ZKP. The ZKP and the front end that calls the API server's API to display and verify DID as well as verify the H. I don't have time to show you the application in action, so I'll show you the screen design I created with Figma. There are various projects that focus on digital identity and trust, so I will provide a brief summary of them. There are the Decentralized Identity Foundation, Hyperledger, LF Decentralized Trust, and DID.com, which focus on decentralized self-sovereign identity using DID and VC. And the EU has a digital identity regulation, EIDAS 2.0. Apart from DID, there is OpenID Connect Identity. In Japan, there is the trusted web of the digital agency and the originator profile of the Originator Profile Technology Research Association. On Ethereum, efforts to build identity systems using DID and VC while protecting privacy using GKP on public blockchains such as GK Passport, Private ID, and Sysmo Connect are actively being carried out. After developing GKVC, the next important step is to implement a trust layer on it. The trust layer will be placed on top of Web2 social media. I'm planning to add 4 functions in the trust layer. The first function is related to identity, which evaluates trust based on the social graph that is connected to Web2, Web3 accounts and DIDs. The second function is related to credentials, which evaluates trust based on the verification of credentials and selective disclosure of credentials. The third function is related to reputation, which evaluates trust by showing GKP ratings based on online activity. The fourth is governance function, which involves people, and I'd like to evaluate trust using DAOs and fact-checking tokens. I'll explain the overall image. The lower side is similar to GKVC. The DID is linked to a person's VC and other credentials, which show a person's authenticity. DID is also related to social activities, which can be associated with Web 2, Web 3, and social network activities. Based on these values and activities, GKP are used to evaluate trust while protecting privacy. The trust is then presented to the end user in the form of scores for the person's authenticity, reputation, social activities, and a trust badge on social media. To materialize this image, I brainstormed ideas that could be addressed in the short term and those that required longer term attention. All ideas build on DID, VC, GKPs, and blockchain-based verification. A clear and easy to understand trust display is crucial. Let me outline some short-term ideas, some of which have already been implemented in GKVC. They are DID binding for social media accounts, VC-based profile verification, and trust badges with selective disclosure. Another short-term ideas are blockchain-based timestamping for important posts. Hash the content and record the timestamp on chain. Later prove that the post has not been tampered with. And the GKP of humanity or AI disclosure. Prove I'm a human or this is an AI agent without revealing identity details. Long-term ideas are GK reputation, privacy-preserving trust scores, aggregate on-chain and off-chain activities into a reputation, reveal only that the score is above a threshold, not the exact value, and strong originator proof for content. DID signed originator metadata for images, videos, and text. Improve traceability in the age of generative AI. And decentralized social graph verification. Use DID linked social graphs and GK proofs of relationship strengths. And DAO-based decentralized fact-checking. Fact-checkers are verified by VCs and coordinated by a DAO. Token incentivized trust ecosystems. Use tokens to reward credible behavior and penalize manipulation. Design the mechanism to encourage healthier information flow. In conclusion, the problems I want to solve are implementing services that visualize trust in society. It provides services that reduce the cost of determining the trust of the recipient while protecting the privacy of the person's authenticity, credential, activity performance, and social relationships. It uses cryptographic technology, which enables mathematical verification. It presents multiple axes to indicate trust, encouraging multiple judgments of the recipient. It has a user-friendly UI/UX service. To summarize, I try to solve the issues of Web 2 era social media by applying Web 3 technologies and philosophies. Digital identity is the key, and DID and VC are important. First prototype GKVC was built during the ISA Tokyo hackathon using DID, VC, and GKP. My next plan is to implement a trust layer. My goal is to create a human-centered, cryptographically verifiable digital trust layer that connects Web 2 and Web 3. That's all. Thank you
Thank
for
you.
listening.
Yeah, time for question. Are there any questions?
Thank you very much for the talk, Professor Watanabe. I'm Akihiro. I have one question. So, yeah, you proposed system, ecosystem, maybe is really great, but my question is about the incentive mechanism. Maybe reputation system might be the incentive, but so how everyone use your proposed system, how everyone begin to use, and how everyone try to use continuously. So this is my questions. So if you have some comment to add, could you explain?
Thank you very much for your very important question. The incentive is very important. And I still don't have a concrete idea of how to incentivize the people. I'm now studying mechanism design and token economics.
So to manage the verifiable credential and reputation system on blockchain, maybe if we use public blockchain, we have to pay transaction fee. So only actually, you're right. So we must design incentive mechanism using mechanism design or something like that. So so maybe we can talk offline in any situation later in Japan, maybe. Let's talk about.
Thank you very much. It's very great for me.
Yeah, actually, your talk is very interesting because in the past I tried to begin DAO, decentralized autonomous organization, to support fact checker to prevent fake news. So I think we are very cross interest. So let's maybe later in Japan, let's talk someday.
Okay.
Thank you very much.
I appreciate it very much. Thank you, Professor Kishiro.
Okay. Thank you, Professor Watanabe, for the insightful talk. So let us thank again. And let us move to the next talk. Next speaker is Professor R.K. Samasundar. He will be talking online. So his talk is on security risk of centralized trading to decentralized finance. So Professor Samasundar.
Am I audible?
Yes, yes.
Where is the sheet? Entire screen.
The up arrow button at the bottom.
Okay. Can you see my slides?
Yes.
Hello? Yeah?
Yes.
Thank you. Good evening. This is the last talk of the day and a long day. So I will try to reduce rather than giving a SOK. Anyway, time is not there. I'll try to highlight some of the important things that need to be considered as the risks kind of a thing are there. So now here, if you look at it, now just let us take a brief look on the Ethereum decentralized blockchain network, and it's a software platform because it has this smart contracts. Technically, it's a second generation. You have stable coin, and also you have the POW version, scalable with respect to compared to Bitcoin, and still large energy consumption. However, you have the smart contract vulnerability, fairness issues, which possibly I will not go into some of the details, but I will get into the MEV kind of a thing. Dynamic supply of coins, the new ETH is issued to reward validators in the POS, while a portion is burned with every transaction. It's a scalable smart contract exploitation, this one. So now here, if you look at the POS stake, it is more secure, less energy intensive. In the POS, they prove that the validators have put something of value into the network that can be destroyed if they act dishonestly. That is the basic thing. Now, this is the question that whether it can be completely automated and how it could be done is the main question that comes into the picture. Validators explicitly stake capital in the form of ETH, and once activated, validators receive new blocks and transactions delivered in the blocks are re-executed. Validator sends a vote called the attestation in favor of the block. Now, if you look at the Ethereum POS, the timing of blocks is determined by the mining difficulty in the POW version. In the POS, the tempo is fixed. Time is POS Ethereum divided into slots, 12 seconds and epochs of 32 slots. One validator is randomly selected to be a block proposer in every slot. This validator is responsible for creating a new block and sending it out to other networks on the network. Also, in every slot, a committee of validators is randomly chosen, whose votes are used to determine the validity of the block being proposed. Dividing the validator setup in committees is important for keeping the network load manageable. Committees divide up a validator set so that every active validator in every epoch, but not in every slot. So now here, the transaction execution, user creates, signs a transaction with his private key, defines the amount of gas, tips get paid to the validator, transaction execution is done kind of a thing. So this means they allow them to organize in upcoming blocks for a maximum profit, and that's how maximum extractable value becomes a part and part of the POS Ethereum kind of a thing or the other. So now here, one of the validator nodes will be the block proposer, having previously been selected pseudo randomly. This node is responsible for building and broadcasting the next block. The node is made up of three parts: execution, consensus, and a validator client. These things I will skip it for lack of time. The transaction can be considered finalized if it has become part of a chain with a supermajority link between two checkpoints. Checkpoints occur at the start of each epoch, and they exist to account for the fact that only a subset of active validators attest in each slot, but all active validators attest across each epoch. Therefore, it's only between epochs that a supermajority link can be demonstrated, and this is where 66% of the total staked ETH on the network agrees on two checkpoints. Crypto economic security, if you look at it, running a validator is a commitment. Validator is expected to maintain sufficient hardware. In return, the validator is paid in ETH. Participating as a validator also opens new avenues for user to attack the network for personal gain and sabotage. Validators miss out on ETH rewards if they fail to participate when called upon, and their existing stake can be destroyed if they behave dishonestly. Two primary dishonest behaviors are proposing multiple blocks and also submitting contradictory attestation. So now here, what it would mean by slashing, amount of ETH slashed depends on how many validators are also being slashed. There is a correlation penalty, etc. I will not go into some of these details. The fourth choice is another important thing. Network performs optimally and honestly only one new block at the head of the chain on and all validators attest to it. However, it is possible for validators to have different views of the head of the chain due to network latency or because a block proposer has equivocated, and therefore consensus client required an algorithm to decide which one to favor. One of the most important things has been the LMD or the ghost. Now, if you look at the POS and the security, 51% attacks still exist, but riskier for the attackers. Attacker would need 51% of stake ETH, could then use their own attestation to ensure their preferred fork was the one with the most accumulated attestations. The weight of accumulated attestations is what consensus clients use to determine the correct chain. The strength of POS is community has flexibility in mounting a counter attack. For example, honest validators could decide to keep building on the minority chain and ignore the attacker's fork while encouraging apps, exchanges, and pools to do the same. They could also decide to forcibly remove the attacker from the network and destroy their staked ETH. These are strong economic defenses against a 51% attack. Long-range attacks, although the finality gadget neutralizes this attack vector, short-range reorganization, although proposer boosting and attestation deadlines mitigate this, bouncing and balancing attacks are also possible. Avalanche attack, overall POS is more secure than the POW. Now, what are the pros? Staking easy for individual participation, promoting decentralization. Staking is more decentralized. Economies of scale do not apply in the same way as for POW. Mining, in the cons are POS is younger, less tested than POW, and POS is more complex to implement. Now, again, continuing with the pros, POS is more crypto economic secure, less issuance of new ETH is required to incentivize network, whereas the cons are users need to run 3 pieces to participate, and MBB is a problem, and this is a double-edged sword in the decentralized finance. So you have advantages of these things or the other. Now let us moving into this one. I think in the morning people had exposure to MGB. I will skip it just to say, because you have a stakeholders in the blockchain, you have the miners, a user who monitors, and Ethereum. This adds to the stakeholders, and this becomes another issue kind of a thing. Attacks by additional stakeholders. Any regular user who runs a full node Ethereum can front run pending transactions by sending adaptive transactions with a higher gas price. A well-positioned relaying node on the network can attempt to influence how transactions are propagated through the network, which can influence the order of transactions received by the miner. It is a classic front-running attack, a sandwich attack, and a back-running attack also has a problem on the network itself because it hinders the throughput of the transactions. Of course, MEV can be exploited using the Bellman-Ford algorithm. I will not go into detail. The question is that how do we mitigate the MEV? Plus point is encourages actors to market inefficiencies to stability, negative ramifications at both the application and network levels. Even potential blockchain reorganizations can happen if the MEV outweighs standard block rewards. This is something. Fair trade is preserved through legal laws, run laws in the classical trades. Insider transaction all the time, regulatory boards require insiders to file reports which are public. And now you know major issue is public information disclosure. Absolute disclosure is not possible. Now the question is that how do we mitigate the uncertainty, the MEV kind of a thing? We have lots of uncertainties in the Ethereum blockchain transactions, including the POS, and now it is the general blockchain, and this is the classic thing what I already said. Now the main issues, let us consider the main things. Issues for realizing MEV resilient As mempool transactions are publicly visible, the life cycle of transactions on a blockchain can be misused by a miner, because he knows he can introduce sandwich, front run, and all this kind of a thing. It is the reordering that comes into the picture, including smart contracts can have embedded bribing miners and so on and so forth. What is the way to mitigate MEB in blockchain? Make the set of transactions in mempool private, prevent the miners from reordering the transactions, or enforce fairness or transaction execution. What is the issue? Now, if you look at realizing mempool privacy, it's not always possible, because if there is a fork, there will be a problem. And now earlier issues has been overcome by batched threshold encryption, as long as a forking is not there, kind of a thing or the other. And now here, if you look at threshold public encryption, it overcame earlier issues of mempool privacy only when they evaluated the things which were not used came back. Otherwise, it was not coming, kind of a thing or the other. It overcame issues of malleability and pending transaction. Some of these things I have communicated in the XRPL presentation. I will not go into some of the details. And now, just to give an automated market marker, what would be the problem in an XRPL, for example? Minor extractable value is the value participant can happen. And now here, robust AMM on XRPL uses batched threshold encryption on XRPL, and now works well with XRPL, does not fork under the 80% similarity consensus, which we have proved earlier. And XRPL, if it satisfies the 80% similarity, it avoids fork, and thus you can overcome the privacy kind of a thing. Of course, what happens with fork formation, the block when eliminated has to be decrypted before sending into mempool, hence privacy is not preserved. Thus in blockchain platforms like Ethereum, difficult to preserve privacy using BTE. So now deficiencies of other mitigation techniques, relative ordering of transactions, enforcing a relative order requires building a dependency graph that enables partial orders on transactions, adapting techniques prevalent in concurrency control. Such systems have again been shown to be prone to front-running attacks. Randomizing transaction ordering shown to be not sufficient. Absolute timestamping transaction. Hedron hash graph is an example. In the morning, I showed you that how, even though MEB is minimized, there is always a possibility, kind of a thing or the other. Randomized sharding minimizes on a restricted class of blockchain platforms, privacy preserving smart contracts. This was something which was used a few years back, but it has a very limited thing, because it can be applied for only a limited class of contracts with the user annotation, which cannot be generalized to general contract written in Solidity, kind of a thing or the other. So now one of the main things that comes into the picture is the proposer-builder separation, a market-based mechanism where external actors known as builders create bundles of complete block contents, including the fee of the proposer. The proposer selects the bundle with the highest fee, introducing a more competitive and efficient system. Aim of the approach is to decentralize the power of block proposers and enhance the network. Issues are exact mechanics of who can all become block proposers under PBS is quite complex, as it needs to address issues of fairness and prevent collusion among stakeholders. As in the morning I showed, the header collusion can lead to MEB. In the proposer builder separation, if you look at it, in the POW, a new block becomes part of the canonical chain. In the POS in the Ethereum, a new block receives attestations. MEB problems arise due to combination of block producer and block proposer. Roles consensus nodes are incentivized to trigger chain reorganization in time-bandit attacks to maximize MEB. What are the pros? In the decentralized task, rely on economically rational actors to ensure the usefulness and stability of their protocols. With DEX arbitrage ensures that users get the best, most correct prices for their tokens, and lending protocols rely on speedy liquidations when borrowers fall below collateralization ratios to ensure lenders get paid back. Without rational searchers seeking and fixing economic inefficiencies and taking advantage of protocols' economic incentives. DeFi protocols, dApps in general, may not be as robust as they are today, and now application layer sandwich trading result in an unequivocal worse experience for users. Users sandwiched face increased slippage, network layer, generalized front runners, and the gas price auctions and high gas prices for everyone else relying to run regular transactions. Between blocks, if the MEV available in a block significantly exceeds in the standard block reward, validators may be incentivized to reorganize blocks and capture the MEV for themselves, causing blockchain reorganization and consensus instability kind of a thing. So in the proposer builder separation designed to mitigate the impact at the consensus layer, major feature is the separation of block producer and block proposer. Validators are still responsible for proposing and voting on blocks, but a new class of specialized entities called block builders are tasked with ordering transactions, building blocks. Under PBS, a block builder creates a transaction bundle and places a bid for its inclusion in a beacon chain block. The validator selected to propose the next block then checks the different bids and chooses the bundle with the highest fee. PBS essentially creates an auction market where builders negotiate with the validators selling the block space. Current PBS designs uses a commit reveal scheme in which builders only publish a cryptographic commitment to a block's content along with their bids after accepting the winning bid. The proposer creates a signed block proposal that includes the block header. The block header is expected to publish the full block body after seeing the signed block proposal, and it must also receive enough attestation from validators before it is finalized. Rewards and fees, you have what is in the Bitcoin and the Ethereum. In the MEV status, extraction ballooned in 2021, extremely high gas prices, emergence of flashbots MEV relay has reduced the effectiveness of generalized front runners and has taken gas price auctions off-chain, lowering gas prices for our users, while many searchers are still making good money from MEV as opportunities become more well-known and more searchers compete for the same opportunity. Validators will capture more and more total MEV revenue. MEV is also not unique to Ethereum, and as opportunities become more competitive on Ethereum, searchers are moving to alternate blockchains like Binance, a smart chain, where similar MEV opportunities as those on Ethereum exist with less competition. Transition from POW to POS, the ongoing effort to scale roll-ups. I think this one is Tessone's group is giving a talk. All change the MEV landscape in ways that are still somewhat unclear. How does guaranteed block proposers known slightly in advance changes the dynamics of MEV extraction compared to the probabilistic model in POW, or how this will be disrupted when single secret leader and distributed validator technology gets implemented. Similarly, it remains to be seen what MEV opportunities exist when most users' activity is ported away from Ethereum and onto its second roll-ups and shorts kind of a thing or the other. And to conclude, main issues: public availability of the mempool, achieving privacy, there are many difficulties, achieving fairness, this is almost impossible, absolute information disclosure is another issue, and now proposer builder separation is perhaps a rational approach, but it has its own, as I mentioned, lots of challenges and a trust that is involved that need to be looked into. Regulation requires a post-mortem, requires a deep forensics. With that I conclude, and then I'll thank you, and then I'm being the last speaker, and I think I held you for hopefully you have a nice time, and those of you who are staying in Meluha, that's a nice place to hang around. You have lots of places. Thank you. Any questions?
Yeah. Question time. Thisone has a question. Yeah.
Professor Shyamsundar, thank you very much for the very comprehensive presentation on the mess that is all this part of MEVs and the block proposers and also the separation, etc. It is a very difficult topic. My question to you is, you are saying that actually making private the mempools is something that can alleviate this problem. And from one point of view, I understand the reasoning, which is if the mempools are private, it is impossible for someone, for example, to try to front run others.
Yeah.
However, it has the other side of the coin is exactly what is happening now with MEV, that is that there are many transactions that are actually not broadcasted to public mempools because they have a direct link between the mempool, between the one that is producing the block and the people that is emitting these transactions, exactly because they front run. So if the mempools were private, it is true that this would not get worse, but I also do not see why it would get better.
Yeah. I think, the question is that mempool privacy implies some kind of a determinism. So in some sense, if you have a deterministic thing, you can't introduce another new transactions and that you can achieve. But what happens is that there will be, like what I mentioned, honest validators versus dishonest validators. They can use their own mining to continue to hack and later throw out the things of the other. And that's how, in some sense, a PBS scheme has to come with some kind of a trust which will enable us to use the privacy and also the trust, so that I can really say why this one, even though there is a slashing, I had to be sure that he has to be slashed. Is there a way, even though he says he has to be slashed, is there a way he can escape? These are all some things that are not easy to comprehend from the transactions themselves.
Correct. Thank you. Yes, I agree.
Any other question? Okay, if not, let us thank Professor Shyamsundar, and let us also thank all the speakers of these sessions, all the speakers, for a wonderful talks for this session. With this, I just hand over my mic to the organizer.
Thank you, Abhijit. So we'll conclude here today, and we'll visit tomorrow morning at 9 o'clock again, same place. Okay. Yeah.
Thank you, Vishwas.
Thank you, sir. Thank you.